Picture the universe not as a serene, predictable expanse, but as a living, breathing entity that constantly throws curveballs at everything we think we know. It's a place where the fundamental rules of reality seem to bend and twist, where stars can wink out of existence without a single trace, and entire galaxies rotate at speeds that defy all known laws of gravity. These are not mere errors in our telescopes or simple glitches in our data. These are cosmic anomalies, profound mysteries woven into the very fabric of space and time. They are the universe's most provocative questions, whispered across the void, daring us to find the answers. For centuries, we have looked up at the night sky and built our understanding of physics and cosmology on a foundation of elegant theories and predictable patterns. But what happens when that foundation begins to crack? What do we do when the cosmos itself presents us with puzzles that our most brilliant minds cannot immediately solve? This is where true discovery begins. This journey we are about to take together is not just a tour of strange celestial phenomena. It is an exploration into the very frontiers of human knowledge, where each anomaly is a beacon pointing toward a deeper, more complete understanding of everything that exists. These cosmic anomalies are far more than just celestial quirks. They are the catalysts for revolutionary new scientific thought. Every time we encounter something in the universe that shouldn't be possible according to our current models, it forces a profound shift. It pushes physicists and cosmologists to the absolute limits of their imagination, compelling them to draft new equations, conceive of new particles, and even reconsider the nature of reality itself. We will delve into the minds of the scientists who are grappling with these enigmas, feeling the weight of the unknown and the thrill of a potential breakthrough. We will see how a single unexplained drift in a spacecraft's trajectory or a mysterious signal from the depths of space can unravel decades of accepted theory and ignite a firestorm of new ideas. This is the process by which science truly evolves, not through the steady accumulation of facts, but through the disruptive, exhilarating confrontation with the things we cannot explain. It is in these gaps in our understanding that the future of physics is being written, so prepare to have your perspective on the cosmos completely transformed. As we dive into the unknown together, from the ghostly influence of dark matter to the baffling acceleration of the universe's expansion, you will see how every mystery, every anomaly holds a key. It is a key that may unlock a deeper truth about our existence, from the smallest quantum particle to the vast, sweeping structure of the cosmic web. This is an invitation to join a grand adventure, to witness firsthand how the greatest wonders of the universe are often hidden in its most perplexing puzzles. Get ready to rethink everything you thought you knew about space, time, and our place within it all. Think of a cosmic anomaly not as a mistake, but as a cosmic whisper, a subtle clue that the universe is far more complex and wondrous than our textbooks suggest. At their heart, these anomalies are simply deviations from what our most trusted scientific models predict should happen out there in the void. Imagine you're an astronomer and you point your telescope at a massive galaxy cluster. You know how its gravity should bend the light from objects behind it, a phenomenon called gravitational lensing. You've run the calculations based on Einstein's theory of general relativity. But when you look at the data, the light is bent in a way you just can't explain with the visible matter you see. That discrepancy, that unexpected twist in the story of light, is a cosmic anomaly. It's the universe telling you that your map is incomplete, that there's something missing from your understanding of gravity or matter itself. These puzzles pop up everywhere, from the faint afterglow of the Big Bang to the peculiar motions of distant spacecraft. They are the unresolved notes in the symphony of the cosmos, and for scientists, they are the most exciting part of the job. What makes an anomaly truly significant is its power to challenge the very foundations of physics. It's one thing to have a small measurement error. It's entirely another to encounter a result that seems to break the rules we thought were set in stone. Consider the axis of evil, a rather dramatic name for a pattern found in the cosmic microwave background, the oldest light in the universe. This relic radiation should be essentially the same in every direction, a fundamental assumption known as the cosmological principle. Yet the data reveals a strange alignment, a preferred direction that hints the universe might not be as uniform as we believed. This isn't just a statistical blip, it's a direct confrontation with a core tenet of modern cosmology. Similarly, when particles behave in ways the standard model can't account for, or when the expansion rate of the universe measured nearby doesn't match the rate calculated from the ancient universe, we are forced to reconsider our most basic assumptions about reality. These aren't problems at the edges of science, they are challenges aimed at its center. Unraveling these mysteries is a monumental task that requires a three-pronged attack, blending the best of observation, theory, and computation. Observational astronomers are the detectives, collecting the evidence with ever more powerful telescopes and sensors. They gather the light, the radio waves, the X-rays, and the gravitational waves that form the crime scene of the cosmos. Then, theoretical physicists step in to be the profilers, trying to concoct new explanations, new laws of physics, or new types of particles that could account for the strange evidence. Could it be dark matter, a modification of gravity, or something we haven't even dreamed of yet? Finally, computational scientists build incredibly complex simulations, virtual universes where they can test these new theories against the data, helping to separate the genuine signals from the overwhelming cosmic noise. This collaborative, multidisciplinary effort is how we separate the fleeting statistical flukes from the truly revolutionary discoveries that have the potential to redefine our place in the cosmos. By carefully studying the characteristics of each anomaly, scientists can judge which ones are likely to lead to a true paradigm shift, setting the stage for the deep and specific mysteries we are about to explore. Now, let's journey back to a mystery that began not in the distant cosmos, but right here in our own solar system, with two robotic pioneers venturing into the unknown. The Pioneer 10 and Pioneer 11 spacecraft, after completing their primary missions to Jupiter and Saturn, continued on trajectories that would eventually carry them out of the solar system entirely. They were humanity's first emissaries on a one-way trip to the stars, but as they traveled farther and farther from the Sun, drifting through the cold, dark expanse beyond the orbit of Pluto, something peculiar happened. Flight controllers tracking the spacecraft with incredible precision noticed a tiny, unaccountable drift. Both pioneers were experiencing a very slight but persistent deceleration. It was as if an invisible hand was gently applying the brakes, pulling them back toward the inner solar system. This minuscule force was equivalent to just 10 billion times weaker than the gravity we feel on Earth's surface, an effect so small you'd think it could be ignored. Yet it was there, a stubborn signal in the data that refused to go away, and it simply could not be explained by the known physics of the time. This tiny discrepancy sparked a debate among scientists and engineers that would last for decades. How could these spacecraft, coasting through the near vacuum of space, be slowing down? The immediate suspicion fell on the spacecraft themselves. Perhaps it was the gentle, unseen push of heat. The Pioneers were powered by radioactive thermoelectric generators, and they generated waste heat that radiated away from the spacecraft. The hypothesis was that if this heat radiation was not perfectly uniform, if it was slightly stronger in one direction specifically, radiating more from the warm side facing the sun, it could create a tiny thrust pushing back against the direction of travel. This concept, known as anisotropic thermal radiation pressure, became a leading candidate, but other, far more exotic ideas were put on the table. Could it be the gravitational pull of an unknown, unseen planet lurking in the outer darkness? Was it the drag from a diffuse cloud of dark matter enveloping our solar system? Some physicists even proposed that this was the first observational hint that our understanding of gravity itself was flawed, suggesting modifications to Einstein's theory of general relativity that would only become apparent over vast interplanetary distances. The Pioneer Anomaly became a playground for the imagination, where conventional engineering met the edges of theoretical physics. To solve this puzzle, researchers embarked on a monumental forensic investigation, digging through decades of old telemetry data. They had to account for every conceivable influence, from the subtle pressure of the solar wind to the gravitational tugs of countless known asteroids. They built increasingly sophisticated models of the Pioneer spacecraft, simulating how heat flowed through their metal bodies and radiated into space. This was a masterclass in meticulous scientific detective work, separating an incredibly faint signal from an immense amount of noise. After years of analysis, the consensus gradually coalesced around the thermal explanation. The primary cause was indeed the anisotropic radiation of heat, the spacecraft's own warmth, bouncing off their equipment and antennae in a slightly unbalanced way, was providing just enough recoil to produce the observed deceleration. It was a brilliantly mundane solution to a seemingly profound mystery, but to view the Pioneer story as a simple case of a solved problem is to miss its true, enduring legacy. The fact that scientists spent decades chasing down a force 10 billion times weaker than gravity speaks volumes about the power of precision measurement. It demonstrated that by paying exquisite attention to the smallest details, we can uncover subtle phenomena that would otherwise be completely invisible. This pursuit forced the development of more rigorous data analysis techniques and instilled a culture of extreme caution in planning future missions, like the legendary Voyager probes. The anomaly, even in its resolution, taught a powerful lesson: never dismiss a tiny discrepancy. What appears to be a minor glitch today could be the first whisper of a fundamental truth tomorrow. The story of the Pioneer Anomaly is a testament to scientific perseverance, showing us that the path to deeper understanding is often paved with the most patient and precise examination of the things that at first just don't seem to add up. While the Pioneer Anomaly was a mystery confined to our own cosmic backyard, the next great enigma we must confront is one that pervades the entire universe, an invisible component so vast that it outweighs all the stars, planets, and galaxies we can see. This is the profound puzzle of dark matter. Think of everything you have ever seen in a telescope or admired in a photograph of the night sky, every glittering star, every swirling galaxy, every luminous nebula. Astonishingly, all of that, all the ordinary matter made of atoms, accounts for less than 5% of the total content of the cosmos. Dark matter, which neither emits, absorbs, nor reflects any light, makes up about 27% of the universe. It is a ghostly presence, a cosmic scaffolding that holds the visible universe together through gravity alone, yet it remains utterly invisible to our eyes and our telescopes. We cannot see it, but we can feel its gravitational pull, a force that sculpts the cosmos on the grandest scales. The evidence for this unseen mass is compelling and comes from multiple, independent lines of observation. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a massive gathering of galaxies, and noticed something bizarre. The individual galaxies were moving so quickly that the cluster's own gravity should not have been strong enough to hold them together. Based on the amount of visible matter, the entire cluster should have flown apart long ago. Zwicky proposed the existence of dunkle materie, or dark matter, to provide the missing gravitational glue. Decades later, Vera Rubin provided even more concrete evidence by meticulously mapping the rotation curves of spiral galaxies. She found that stars at the outer edges of galaxies were orbiting just as fast as those near the center, a finding that defied the laws of gravity as we knew them. According to Kepler's laws, these outer stars should have been moving much more slowly, like distant planets in our solar system. The only logical explanation was that each galaxy was embedded within a massive, invisible halo of matter, its gravity whipping the stars around at those unexpected speeds. This halo, this dark matter, provides the extra gravitational pull that keeps galaxies from spinning themselves apart. Beyond individual galaxies, dark matter's signature is written across the large-scale structure of the entire universe. When we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see tiny temperature fluctuations that are essentially a blueprint for all the structure that would later form. The patterns we see are perfectly explained if a type of cold, slow-moving dark matter was present, acting as a gravitational anchor around which ordinary matter could coalesce. Furthermore, the way massive galaxy clusters bend the light from more distant objects, an effect known as gravitational lensing, reveals an even more dramatic picture. The amount of lensing we observe is often far too strong to be caused by the visible matter in the cluster. It's as if we are looking at a landscape through a warped piece of glass, and the distortion tells us that there is a tremendous amount of invisible mass warping the fabric of spacetime itself, bending the light on its journey to us. For decades, the leading candidates for what dark matter could have been WIMP, or weakly interacting massive particles. These are hypothetical particles that don't interact with light or ordinary matter very often, but have a significant mass, making them perfect for the role of the universe's invisible backbone. To find them, scientists have embarked on a two-pronged attack. The first approach is to try and create them. At the Large Hadron Collider, physicists smash protons together at nearly the speed of light, hoping that the immense energy of these collisions will briefly conjure dark matter particles into existence. The second approach is to try and catch them directly, in deep underground laboratories shielded from cosmic rays by thousands of feet of rock. Incredibly sensitive detectors wait in the cold and dark. These instruments, often filled with ultra-pure liquid xenon, are designed to feel the faintest ping, the minuscule recoil that would occur if a dark matter particle were to ever, very rarely, bump into the nucleus of an atom. Despite these heroic efforts and decades of searching, these detectors have remained silent. We have not yet directly captured a single dark matter particle, which only deepens the mystery. This persistent failure to find a direct particle has led some physicists to propose a radically different solution. What if dark matter doesn't exist at all? What if instead our understanding of gravity is simply wrong on the scale of galaxies? This is the premise of modified Newtonian dynamics, or MND. Proposed by physicist Mordechai Milgrom in the 1980s, MND suggests that the laws of gravity change when its pull becomes incredibly weak, such as in the outer reaches of galaxies. Under this theory, there is no need for invisible matter. The strange rotation curves of galaxies are just a consequence of gravity behaving differently than Einstein or Newton predicted. While MND does a surprisingly good job at explaining the motions within individual galaxies, it struggles to account for all the evidence, particularly the gravitational lensing by galaxy clusters, and the precise patterns in the cosmic microwave background. The majority of the scientific community still leans towards the dark matter hypothesis, but the existence of MUND highlights a crucial point. The dark matter puzzle is so profound that it forces us to question our most fundamental understanding of the universe. Are we missing a type of particle, or are we missing a deeper law of physics? This is the true power of the dark matter enigma. It is not just a single missing piece. It is a gateway that pushes cosmology into the realm of the truly exotic. If dark matter is a particle, it must be something entirely outside the standard model of particle physics, pointing toward a whole new world of subatomic reality. Theorists are now considering possibilities like multi-dimensional theories, where gravity leaks into other dimensions, or exotic particles like actions, which were originally proposed to solve a different problem in quantum physics. The quest to find dark matter is more than just a hunt for a single particle. It is a journey to understand what the vast majority of our universe is actually made of. Every null result from an underground detector, every new, precise map of a galaxy's rotation, and every innovative observation of gravitational lensing brings us closer to an answer, driving a cycle of innovation in both our theoretical ideas and our experimental technology that continues to reshape our view of the cosmos. Just as we grappled with the invisible pull of dark matter, a discovery at the close of the 20th century revealed a force of an entirely different and far more counterintuitive nature. For decades, the prevailing view of the cosmos's future was a relatively simple one. After the explosive violence of the Big Bang, the universe had been coasting outward, its expansion gradually slowing down over billions of years under the relentless collective pull of gravity from all the matter within it. The central question for cosmologists was whether there was enough matter to eventually halt that expansion, leading to a big crunch, or if the universe would simply keep expanding forever, albeit at a slower and slower pace. Then, in the late 1990s, two independent teams of astronomers made a measurement that would shatter this foundational assumption and turn cosmology on its head. They were studying a specific kind of stellar explosion, a Type 1 supernova, which acts as a standard candle. Because these supernovae always explode with roughly the same intrinsic brightness, astronomers can measure how bright they appear from Earth and precisely calculate their distance. Furthermore, by analyzing the redshift of their light, how much it has been stretched as the universe expands, they can determine how fast the universe was expanding when the star blew up. The teams expected to see that the most distant, and therefore oldest, supernova were receding from us faster than the models predicted, showing the deceleration from a younger, more energetic universe. Instead, they found the exact opposite. The distant supernova were fainter than they should have been, meaning they were farther away than anyone had calculated. The inescapable conclusion was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was actively pushing galaxies apart, overwhelming the collective grip of gravity. This revelation was so profound and so unexpected that it earned the leaders of the two research teams the Nobel Prize in Physics in 2011. The discovery fundamentally rewrote the story of our cosmos. The universe wasn't just a passive backdrop for galaxies and stars. It contained a dynamic, dominant component that was dictating its long-term evolution. This mysterious agent was given a name that reflected our profound ignorance of its true nature: dark energy. When cosmologists added up the entire energy budget of the universe, they arrived at a composition that is both humbling and awe-inspiring. All the ordinary matter, the stuff of stars, planets, and life, accounts for a mere 5%. Dark matter, the invisible gravitational glue, makes up about 27%. The remaining 68%, the overwhelming majority of everything that exists, is dark energy. It is the primary driver of the cosmos's behavior, an unseen force woven into the very fabric of space-time that is causing the universe to fly apart at an ever-increasing rate. So, what could this enigmatic force possibly be? The leading candidate is an idea that Albert Einstein himself first proposed, and then later famously discarded as his greatest blunder. In his equations of general relativity, Einstein included a term called the cosmological constant, represented by the Greek letter lambda. He originally inserted it to achieve a static universe, which was the prevailing belief at the time, as a counterbalance to gravity that would prevent the cosmos from collapsing under its own weight. When Edwin Hubble later discovered the universe was indeed expanding, Einstein abandoned the concept, but with the discovery of the accelerating expansion, the cosmological constant was resurrected. In this modern context, it represents a constant energy density inherent to the vacuum of space itself. Think of empty space not as a true void, but as a seething, bubbling foam of virtual particles that constantly pop in and out of existence. This vacuum energy is theorized to generate a kind of negative pressure, a repulsive gravity that pushes the universe apart. The problem, however, is one of catastrophic proportions. When quantum field theorists calculate the predicted strength of this vacuum energy, the number they get is about 120 orders of magnitude. That's a 1 with 120 zeros after it, larger than the value astronomers actually observe. This is the single worst prediction in the entire history of physics, a discrepancy so vast it tells us we are fundamentally missing something crucial. This immense failure of theory has led scientists to explore other compelling ideas. One of the most prominent alternatives is a concept known as quintessence. Named after the fifth element of ancient Greek philosophy, quintessence proposes that dark energy is not a constant but a dynamic field that permeates all of space. Unlike the static cosmological constant, this field could change in strength and density over time. It could even interact with other forms of matter and energy. In some quintessence models, the repulsive force we see today was weaker in the past and could become stronger or weaker in the future. This introduces a thrilling and somewhat unsettling unpredictability into the ultimate fate of the cosmos. Another, more radical school of thought suggests that we may not need dark energy at all. Instead, the apparent acceleration could be a sign that our theory of gravity, Einstein's magnificent general relativity, begins to break down on the very largest cosmic scales. Just as Newton's gravity needed an update for extreme speeds and strong gravity, perhaps Einstein's theory requires modification when applied to the entire visible universe. These theories, often called modified gravity models, attempt to tweak the equations of relativity to explain the observations without invoking a mysterious dark energy component, though none have yet proven entirely successful. The enigma of dark energy, therefore, strikes at the very heart of our understanding of physics, forcing a confrontation between our two most successful and yet incompatible theories, quantum mechanics and general relativity. It challenges our comprehension of fundamental forces and pushes us to contemplate the ultimate destiny of everything we see. If dark energy is indeed a constant cosmological constant, then the acceleration will continue indefinitely. In this future, often called the heat death or big freeze, the universe will expand at an ever-increasing pace. Galaxies beyond our own local group will be pushed away until their light can no longer reach us, leaving our night sky empty and black. Eventually, all stars will burn out and matter itself may decay, leaving a cold, dark, and utterly dilute cosmos. However, if dark energy is something more dynamic like quintessence, other fates are possible. A big rip scenario could occur if the repulsive force grows so strong that it tears apart galaxies, solar systems, planets, and even atoms themselves. Or the field could eventually reverse, leading to a deceleration and a potential collapse. As we probe deeper with powerful new telescopes and sky surveys, this great cosmic anomaly continues to inspire and demand new models, reminding us that the greatest secret of the universe's evolution remains hidden in plain sight, driving the next revolution in our understanding of reality. This brings us to a puzzle so fundamental that it has shaken the very foundations of modern cosmology, a disagreement over a single number that threatens to rewrite our cosmic story. This is the Hubble tension. At its heart is the Hubble constant, a value that represents the current expansion rate of our universe. It tells us how fast galaxies are receding from us for every megaparsec of distance, essentially quantifying the speed of the cosmos's ongoing growth. For decades, astronomers have worked to pin down this number with ever greater precision, believing it to be a fixed pillar of our cosmological model. But a profound problem has emerged. When we measure this expansion rate using two of the most trusted and independent methods in all of science, they give us two different, stubbornly incompatible answers. It's as if you used two different, perfectly calibrated rulers to measure the same object and got two distinct results every single time. This isn't a small, marginal error. It's a significant and persistent discrepancy that has created a genuine crisis in our understanding of the universe's evolution. Let's break down where these two conflicting numbers come from. The first method peers back into the deep past, to the very infancy of our cosmos. Scientists use exquisitely detailed maps of the cosmic microwave background, the leftover heat from the Big Bang, captured by missions like the Planck satellite. This ancient light provides a snapshot of the universe when it was only 380,000 years old. By analyzing the subtle patterns in this radiation, the tiny fluctuations in temperature and polarization, cosmologists can work backwards. They can run the cosmic film in reverse, using the incredibly successful lambda-cold dark matter model to simulate how the universe evolved from that dense, hot beginning to the vast structure we see today. This process gives them a predicted value for how fast the universe should be expanding now. It's a method rooted in the physics of the primordial universe. The second method is much more local and direct. Astronomers measure the expansion rate by observing the universe as it is today. They use a cosmic distance ladder to gauge how far away certain objects are. The first rungs of this ladder are nearby stars called Cepheid variables, whose well-understood pulsations allow for precise distance measurements. The next rungs involve Type Ia supernova, which, as we discussed, act as brilliant standard candles. By measuring the distances to these supernovae and their redshifts, astronomers can directly calculate the current expansion rate. The problem is stark and undeniable. The value from the early universe, the Planck measurement, suggests an expansion rate of about 67 kilometers per second per megaparsec. Meanwhile, the local measurement, championed by projects like the SH0ES team, points to a faster rate of around 73. This gap of about 6 or 7 kilometers per second might not sound like much, but given the incredible precision of these measurements, the statistical significance is overwhelming. The chance that this is a simple fluke is astronomically small. The universe, according to its own ancient light and its present-day behavior, seems to be telling two different stories about its own expansion. So, what could possibly explain this rift? Cosmologists are exploring several compelling and some truly exotic possibilities. The first and most mundane explanation is that there are unknown systematic errors creeping into our measurements. Perhaps our understanding of the Cepheid variables is not as perfect as we think, or there's some subtle bias in how we calibrate the cosmic distance ladder that we haven't yet identified. This is where powerful new tools like the James Webb Space Telescope are entering the fray. With its unparalleled infrared vision, JWST is peering through the cosmic dust to observe Cepheids and supernova with unprecedented clarity, aiming to either confirm or eliminate local measurement errors. On the other side, next-generation observatories are scrutinizing the cosmic microwave background with even greater sensitivity, searching for any potential systematic effects that might have skewed our view of the early universe. If the discrepancy holds, as it increasingly seems it will, then we are forced to consider that the problem isn't with our measurements, but with our model. The Lambda-CDM model, the foundational framework of modern cosmology, might be incomplete. This opens the door to thrilling new physics. One possibility is that dark energy is not a constant cosmological constant, but is instead dynamic. Perhaps it's strengthened over the history of the universe, giving the expansion an extra, unanticipated kick that our models based on the early universe didn't account for. Another line of thought points to the potential existence of early dark energy, a new form of energy field that was active for a brief period in the universe's first moments, subtly altering the initial conditions in a way that resolves the tension. Other theories propose new types of relativistic particles that flooded the early cosmos, or even that dark matter possesses properties more complex than we currently assume, such as the ability to interact with itself or with light in ways we haven't detected. The Hubble Tension has effectively turned the entire field of cosmology into a vibrant brainstorming session, where long-held assumptions are being re-evaluated in the quest for a more complete theory. This is more than just an academic debate. It is a powerful demonstration of how science progresses. The Hubble Tension is a gift born from precision. It is because our instruments and techniques have become so extraordinarily accurate that we can now see a crack in our foundational model that was previously invisible. This anomaly is actively driving the development of the next generation of astronomical tools, from gravitational wave observatories that can provide a completely independent measure of cosmic distances, to vast ground-based surveys like the Vera Rubin Observatory that will map the cosmos in unprecedented detail. The tension reminds us that constants may not be so constant, and that our most cherished models are always provisional, awaiting the next discovery that will force them to evolve. It is a humbling and exhilarating reminder that the universe still holds profound secrets, and that the answers we seek may require us to look at the cosmos in a completely new light. Now, let's shift our focus from the grand architecture of the cosmos to the fleeting, brilliant flashes that punctuate the radio silence of deep space. These are fast radio bursts, or FRB, and they are among the most explosive and enigmatic phenomena ever detected. For just a few milliseconds, a source in a distant galaxy can release more energy than our sun puts out over 80 years, all concentrated into a single, powerful pulse of radio waves. The first of these bursts was discovered by accident in 2007, buried in archival data from the Parkes Radio Telescope in Australia. Astronomers were stunned, and for years it remained a solitary, bizarre event that defied explanation. Was it a local glitch, some terrestrial interference, or was it truly a cosmic signal? Since then, we have detected hundreds of these events, confirming that they are indeed real, they are common, and they are happening all across the universe. Each detection is like a cosmic camera flash going off in a dark room, illuminating a tiny piece of the universe for a fraction of a second before vanishing back into the void. The sheer power and brevity of these bursts present a monumental challenge. How can something so energetic happen so fast? This puzzle of power and speed immediately points toward some of the most violent and extreme objects known to astrophysics. The leading suspects are the dense, spinning corpses of dead stars, objects where the laws of physics are pushed to their absolute limit. One prime candidate is the magnetar, a type of neutron star with a magnetic field so unimaginably powerful that it could erase a credit card from hundreds of thousands of kilometers away. Theorists suggest that these objects can experience starquakes, sudden fractures in their rigid crusts, which release titanic amounts of energy in the form of a radio blast. Another compelling possibility is the collision of two neutron stars, a cataclysmic merger that we know also produces gravitational waves. Such an event could potentially unleash a one-time, incredibly bright flash of radio emission. But the plot thickened dramatically with the discovery that not all FRBs are one-off events. Some of them repeat, flashing from the same patch of sky again and again, often with no predictable pattern. This repetition immediately rules out any model that involves the total destruction of the source, like a single, final merger. It means the engine powering these bursts must be able to survive its own outburst and fire again, pushing us toward models involving volatile, rotating objects like highly magnetized neutron stars in complex binary systems. Of course, the sheer strangeness of these signals has also sparked more speculative ideas. The fact that they are so brief, so bright, and concentrated in the radio part of the spectrum has led a few scientists to ponder whether they could be evidence of advanced technology. Could an FRB be the signature of an interstellar lighthouse, a power beam for an alien light sail, or simply a byproduct of a vast, cosmic-scale engineering project? While this is a fascinating thought experiment, the scientific consensus strongly favors natural, albeit extreme, astrophysical origins. The primary reason is that we have now managed to trace many of these bursts, including repeaters, back to their host galaxies. We find them in all sorts of cosmic environments, in massive galaxies, in tiny dwarf galaxies, and even in regions with intense star formation. This diversity suggests that whatever is making them is a universal physical process, not the signature of a single type of civilization. The hunt for their homes has been a triumph of modern astronomy, requiring rapid coordination between radio telescopes that first detect the burst and optical, X-ray, and gamma-ray observatories that swiftly swing into action to identify the source galaxy. This collaborative effort has transformed FRBs from mere curiosities into valuable tools for cosmic exploration. This is where the story of fast radio bursts takes a remarkable turn, transforming them from a mystery to be solved into a key that can unlock other secrets. As these radio waves race across millions or even billions of light-years of intergalactic space, they don't travel through a perfect vacuum. They pass through a diffuse, ionized gas known as the intergalactic medium, as well as the halos of galaxies and other cosmic structures. This material leaves a distinct fingerprint on the radio signal, causing the different frequencies within the burst to spread out or disperse, with the lower frequencies arriving slightly later than the higher ones. By measuring this dispersion, astronomers can effectively count the total number of electrons the signal encountered on its journey to Earth. This provides a unique way to measure the amount of normal, baryonic matter that is distributed between galaxies, matter that is incredibly difficult to detect by any other means. In a very real sense, each FRB acts as a cosmic dipstick, gauging the density of the material that fills the vast voids and filaments of the cosmic web. With enough of these bursts, we can build a three-dimensional map of where the universe's missing ordinary matter is hiding, directly addressing one of the other great anomalies we've discussed. The relentless pursuit of these millisecond mysteries is driving a technological revolution in how we observe the sky. Because FRBs are so brief and unpredictable, astronomers have had to develop sophisticated real-time detection systems. Modern radio telescopes, like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, are essentially super-powered digital cameras for the radio sky. They scan vast swaths of the heavens continuously, their powerful computing systems running algorithms that can instantly recognize the unique signature of a fast radio burst amidst the constant background noise of terrestrial radio interference and other cosmic sources. The goal is to issue an alert within seconds, triggering a global network of other observatories to train their instruments on the same location. This is the burgeoning field of multi-messenger astronomy, where we don't just look with one type of light. We combine the radio detection with searches for associated signals, a simultaneous flash of gamma rays, a pulse of X-rays, or even a ripple in space-time from a gravitational wave. By catching an FRB in the act with multiple different eyes, we can finally pin down the exact engine that drives it. Every new detection, every new repeater that is identified, adds another crucial piece to the puzzle, bringing us closer to understanding the lives and deaths of the most magnetic and dense objects in the universe, and in the process, illuminating the invisible structure of the cosmos itself. But while we study these brief flashes from across the cosmos, our own galactic home is caught in a vast and relentless river of motion, pulled by a hidden force whose source remains one of the great navigational puzzles of the universe. For decades, astronomers have known that our Milky Way galaxy is not simply drifting aimlessly through the void. It is moving at a staggering speed of over 2 million kilometers per hour in a very specific direction, a trajectory that includes not just our galaxy but the entire local group of galaxies, all seemingly drawn toward a single point in the depths of space. This mysterious gravitational focal point was named the Great Attractor, and it represents a profound anomaly in our map of the nearby cosmos. Imagine you are floating in a vast, gentle river, and you can feel a persistent current pulling you toward a waterfall hidden by a dense, impenetrable fog. You can't see the waterfall, but you can feel its irresistible tug. That is the position we find ourselves in with the Great Attractor. We can measure our motion, we can feel the pull, but the source of that pull is largely obscured from our view, hidden behind the bright, dusty disk of our own Milky Way, in a region of the sky astronomers call the zone of avoidance. The very existence of such a concentrated pull challenges our understanding of the cosmic web, the large-scale structure of the universe that resembles a vast network of galaxies separated by enormous voids. According to the principle of homogeneity, matter should be distributed fairly evenly on the grandest scales. Yet here, in our own cosmic backyard, we have evidence of a colossal concentration of mass, a gravitational sinkhole so powerful it can dictate the motion of thousands of galaxies. The initial discovery came from studies of the cosmic microwave background. This primordial light creates a universal reference frame, and by measuring our motion relative to it, scientists detected a peculiar velocity, a deviation from the smooth expansion of the universe that pointed directly toward the constellation Centaurus. This wasn't just the Milky Way moving on its own. Our entire local sheet of galaxies was flowing en masse toward this unseen attractor, a motion that became known as the bulk flow. The question became terrifyingly simple. What could possibly be massive enough to cause this, to pierce the veil of the Milky Way's own obscuring dust and stars? Astronomers had to turn to eyes that see in wavelengths invisible to our own. Infrared telescopes like the pioneering Infrared Astronomical Satellite and later the Spitzer Space Telescope could peer through the cosmic dust, revealing the faint glow of galaxies hidden behind the galactic plane. Even more revealing were X-ray observatories, which detected the high-energy emission from incredibly hot gas often found at the hearts of massive galaxy clusters. What these observations revealed was not one single monolithic object, but a complex and dense tapestry of structure. They found that the direction of the Great Attractor coincides with the Norma cluster, a massive gathering of galaxies, and the broader Laniakea supercluster, of which our Milky Way is merely a distant suburb. Laniakea, a Hawaiian word meaning immeasurable heaven, is a filamentary web of galaxies spanning over 500 million light-years, and its gravitational center lies in the general vicinity of the Great Attractor. But the plot thickened further with the identification of an even larger source of gravity lying beyond it, the Shapley supercluster, the most massive concentration of galaxies in our nearby universe. It appears that the pull we feel is not from a single attractor, but from a combination of these immense structures, with the Shapley supercluster acting as a distant, heavyweight anchor intensifying the flow. Yet, even with these discoveries, the full picture remains frustratingly incomplete. When astronomers add up the combined mass of all the known galaxy clusters and superclusters in this direction, it still doesn't seem to fully account for the immense velocity of our bulk flow. This suggests there might still be more mass lurking in the zone of avoidance, vast collections of galaxies or diffuse dark matter that our current telescopes have yet to fully catalogue. This lingering uncertainty is precisely what drives some of the most ambitious sky surveys in modern astronomy. Projects like the Dark Energy Survey and the upcoming Legacy Survey of Space and Time at the Vera Rubin Observatory are not just looking at the distant universe, they are meticulously mapping the three-dimensional positions and motions of millions of relatively nearby galaxies. By measuring their redshifts, how much their light is stretched by the expansion of the universe, scientists can create a dynamic map, not just of where galaxies are, but how they are moving. They can then use subtle distortions from gravitational lensing, where the light from background galaxies is warped by the invisible dark matter associated with these foreground structures, to weigh the entire system. It is a cosmic accounting project on an epic scale, an attempt to balance the books of mass and motion in our local universe. This grand mystery underscores a profound and beautiful concept in cosmology, that by carefully studying our own local motion, we can uncover the global architecture of the cosmos. The Great Attractor is not just a destination, it is a signpost. The peculiar velocity of our galaxy is a single data point that, when combined with the motions of thousands of other galaxies, reveals the underlying gravitational landscape of the cosmic web. It shows us where the dense knots of dark matter and galaxies lie, and how they are connected by vast, invisible filaments. The quest to understand this gravitational anomaly has therefore inspired entirely new methods in observational cosmology, pushing us to combine data across the electromagnetic spectrum and to develop sophisticated computer simulations that can model the growth of these structures over billions of years. It is a powerful reminder that we are not passive observers of the universe, but active participants within a dynamic, flowing cosmos, and by tracing the river of our own motion, we can begin to map the entire continental shelf of the universe. Just as we contemplate the vast currents guiding entire galaxies, we can also turn our gaze inward to the frozen frontier of our own solar system, where a different kind of boundary marker hints at forces we have yet to fully see. Far beyond the orbit of Neptune, in the cold, dark reaches where the Sun is little more than a particularly bright star, lies the Kuiper Belt. This is a vast disk of icy remnants, a population of frozen worlds and building blocks left over from the solar system's formation. For years, astronomers have modeled this belt as a kind of cosmic debris field that should gradually thin out the farther you travel from the Sun. the number of these trans-Neptunian objects should slowly and predictably decrease with distance, like a crowd dispersing from a city center. But observations have revealed something far more dramatic and puzzling. At a distance of about 50 astronomical units from the Sun, that's 50 times the Earth-Sun distance, the population of Kuiper belt objects doesn't just slowly fade away, it plummets. It's as if you were walking away from a bustling town and suddenly, at a specific fence line, you found nothing but empty desert beyond. This sharp, unexpected boundary has been named the Kuiper Cliff, and its existence stands as a direct contradiction to our standard models of solar system evolution. This sudden drop-off presents a classic scientific anomaly, a clear discrepancy between what we expect to see and what is actually there. The gradual depletion model is based on our understanding of how the primordial disk of dust and gas coalesced into planets and then left behind a scattered population of smaller objects. The Kuiper Cliff suggests that this process was either not as peaceful as we thought, or that the story of our solar system didn't end with the formation of the 8 planets we know. There are 2 primary, compelling lines of thought that have emerged to explain this celestial fence. The first, and certainly the most thrilling, is the possibility of an unseen planet. This wouldn't be a small, rocky world like Pluto, but a substantial, perhaps even super-Earth-sized planet, lurking in the profound darkness far beyond the Kuiper Cliff. This hypothetical world has been nicknamed Planet 9, and its gravitational influence could be the very reason for the cliff's existence. The second major hypothesis looks back in time, proposing that the early solar system's formation processes were fundamentally different than we currently believe. Perhaps the protoplanetary disk from which our planets formed had its own intrinsic edge, a drop in density sculpted by the Sun's birth cloud. Or maybe gravitational jostling between the giant planets in their youth, a period known as the Late Heavy Bombardment, violently cleared out this outer region, flinging a vast number of objects into interstellar space or inward toward the Sun, leaving behind the stark boundary we see today. The case for Planet 9 is built upon more than just this one cliff, however. Intriguingly, the orbits of the most distant known objects in the Kuiper belt show peculiar clustering patterns that are difficult to explain by chance alone. These are the extreme trans-Neptunian objects, whose highly elliptical paths take them hundreds of astronomical units from the Sun. If you plot their orbits, you find that their points of closest approach to the Sun, their perihelia, seem to be grouped together in space, and their orbits are tilted in a similar way. This is statistically unusual. The relentless tug of the known giant planets over billions of years should have randomized these orbits. It's as if something is herding them, preventing their orbits from spreading out. Sophisticated computer simulations have demonstrated that the gravitational hand of a distant, massive planet, a world with several times the mass of Earth, on a long, looping orbit thousands of years long, could perfectly account for this shepherding effect. This unseen shepherd's gravity would act as a cosmic sculptor, clearing out a swath of space by either ejecting objects from the solar system or pushing them into these peculiar, clustered orbits, thereby creating the very Kuiper Cliff we observe. The hunt for this potential 9th planet is one of the great modern detective stories in astronomy, a pursuit that combines celestial mechanics with cutting-edge observational technology. You don't find such a faint, slow-moving world by simply pointing a telescope at random patches of the sky. The search begins at the supercomputer, where theorists use the strange orbital clustering of the extreme trans-Neptunian objects to narrow down the possible region of the sky where Planet 9 could be hiding. They calculate vast swaths of potential orbits, creating a celestial treasure map. Observers then use this map to guide some of the most powerful telescopes on Earth. The Subaru telescope on Mauna Kea, with its massive mirror and incredibly wide field of view, has been a workhorse in this search, meticulously scanning the predicted zones for a single, faint point of light that moves slowly against the background of fixed stars. The upcoming Vera C. Rubin Observatory, with its ability to scan the entire visible sky every few nights, promises to be a game-changer. It will not only search for Planet 9 directly, but will also discover thousands of new Kuiper belt objects, providing a wealth of new data to either confirm the orbital clustering or reveal it as a mere observational fluke. This is a painstaking process, like searching for a single specific grain of sand on a vast, dark beach, but the potential reward, the discovery of a new major planet in our own solar system, is immense. What makes the Kuiper Cliff mystery so profound is that it transcends simple planetary science and connects directly to the broader field of cosmology. For decades, our own solar system was the only planetary system we knew. Now, we have discovered thousands of exoplanets orbiting other stars, and we see an incredible diversity of architectures, systems with hot Jupiters close to their stars, planets in tightly packed orbits, and evidence of planetary migration and dynamical instability. The processes that might have formed a Planet 9, such as gravitational scattering by the giant planets in the solar system's youth, or even its capture from another star in the Sun's birth cluster, are likely not unique. The dynamical chaos that might be imprinted in our own Kuiper belt could be a common feature of planetary system formation across the galaxy. By decoding the history written in the orbits of these distant icy bodies, we are not just learning about our own home, we are learning about the common life cycles of planetary systems throughout the universe. The Kuiper Cliff, therefore, is more than a puzzle about our backyard. It is a keyhole through which we can peer into the formative processes that shape worlds everywhere. This ongoing investigation perfectly illustrates the dynamic cycle of modern science, where a single anomaly drives progress on both theoretical and observational fronts. The Kuiper Cliff forces astrophysicists to refine their models of planetary formation and migration, testing them against the stubborn reality of the observed data. It pushes engineers and astronomers to build more sensitive telescopes and develop more sophisticated data analysis techniques to probe the darkest, most distant realms of our own planetary system. Whether the ultimate answer is Planet 9, a revised history of our solar system's tumultuous youth, or something entirely unforeseen, the journey to find out is reshaping our understanding of our cosmic neighborhood. It is a powerful reminder that even in the oldest, most familiar corners of space, there are still fundamental discoveries waiting to be made, and that the maps of our own solar system may still have blank spaces large enough to hide a world. From the gravitational tugs within our own solar system, we now turn to a question that has haunted humanity for generations, a cosmic silence that grows louder with every new world we discover. It's a puzzle famously encapsulated in a simple, lunchtime question asked by physicist Enrico Fermi. Where is everybody? This is the Fermi Paradox, and it presents one of the most profound and unsettling anomalies in our understanding of the cosmos. The logic seems unassailable. Our galaxy, the Milky Way, contains hundreds of billions of stars. A large fraction of those stars are now known to host planets, with many of those worlds orbiting within the habitable zone, that Goldilocks region where temperatures could allow for liquid water. The universe has also been around for nearly 14 billion years, providing an immense amount of time for life to arise, evolve, and potentially develop intelligence and technology. By even the most conservative estimates, the galaxy should be teeming with civilizations, many of which would be far older and more advanced than our own. We should see their ships, hear their broadcasts, or at the very least, see some unmistakable sign of their engineering on a cosmic scale. And yet, when we gaze out into the vast, star-filled night, we are met with an eerie and profound silence. This glaring contradiction between the high probability of extraterrestrial life and the complete lack of any observable evidence for it forces us to confront some of the deepest questions about life, intelligence, and our own future. One of the most compelling frameworks for grappling with this silence is the concept of the Great Filter. This idea suggests that there exists some kind of monumental barrier, a critical evolutionary or technological challenge that is extraordinarily difficult for any life form to overcome on the path to becoming a spacefaring civilization. The terrifying implication of this theory is not that the filter lies ahead of us, but that we may have already passed through it. Perhaps the genesis of life itself from non-living chemistry is the incredibly rare event. Or maybe the jump from simple single-celled organisms to complex multicellular life is the true bottleneck. If this is the case, then we on Earth were simply the astronomically lucky ones, and the galaxy might be filled with sterile worlds and bacterial slime, but never a species that looks up at the stars. The more haunting possibility, however, is that the Great Filter still lies in our future. This is a far more sobering thought. It suggests that the development of advanced technology and global consciousness inevitably leads to a self-destructive outcome. Perhaps every civilization that reaches our level of technological prowess eventually succumbs to its own creations, whether through nuclear annihilation, runaway climate change, engineered pandemics, or a nanotechnology disaster. In this scenario, the silence of the cosmos is a graveyard, a warning of a fate that may await us all. The Great Filter forces us to look in the mirror and ask whether the very intelligence that allows us to ponder the stars also contains the seeds of our own destruction. Beyond this daunting filter, scientists and philosophers have proposed a fascinating zoo of alternative explanations that are no less mind-bending. The zoo hypothesis suggests that advanced civilizations are indeed out there, and they are fully aware of our existence, but they have deliberately chosen to quarantine us, observing humanity as we would a protected wildlife preserve. They are allowing us to develop naturally without interference until we reach a certain level of maturity or wisdom. Another captivating idea is that we are simply living in the wrong time. The universe is ancient, and civilizations may rise and fall like waves on a cosmic shore. We could be a relatively young species in a galaxy where other empires flourished and died out billions of years ago, or we might be an early arrival with the great galactic community yet to awaken. There is also the possibility that space is just too big. The distances between stars are so immense that even for an advanced civilization, interstellar travel might be prohibitively slow and expensive. They could be out there but confined to their own stellar neighborhoods, with the vast gulfs of space acting as an unbridgeable moat. Or their mode of communication could be so advanced, based on quantum entanglement or some physics we haven't yet discovered, that their signals are all around us, but we lack the ears to hear them. We are like a person in the middle of a modern city, trying to find a message by looking for smoke signals, completely oblivious to the radio waves and digital data flooding the air. This paradox has only been intensified and sharpened by the revolution in exoplanet science. In the last 3 decades, we have gone from not knowing if other stars had planets to confirming thousands of them, with estimates suggesting there are more planets than stars in our galaxy. Missions like the Kepler Space Telescope have revealed that rocky planets in the habitable zone are not the exception but the rule. The raw ingredients for life, as we understand it, appear to be common throughout the cosmos. Yet, despite this cosmic real estate boom, our decades-long search for extraterrestrial intelligence, known as SETI, has yielded nothing but silence. This stark contrast has pushed the field of astrobiology to evolve and think more creatively. The search is no longer just for deliberate radio messages beamed into space. Scientists are now hunting for a broader category of evidence called technosignatures. These are signs of technology that could be detected across interstellar distances, whether intentional or not. We could look for industrial pollution in the atmospheres of exoplanets, the telltale chemical signatures of CFCs or nitrogen dioxide that would indicate an active industrial civilization. We could search for evidence of giant engineering projects, like Dyson spheres, vast arrays of solar collectors that a highly advanced species might build around its star to harness all of its energy, which would cause the star to emit an unusual amount of infrared radiation. We could even look for the transient shadows of such megastructures as they pass in front of their host stars. The search has expanded from listening for a hello to looking for the fingerprint of a cosmic-scale civilization going about its business. Ultimately, the Fermi Paradox is far more than a scientific puzzle. It is a profound philosophical mirror that reflects our own hopes, fears, and aspirations. It forces us to contemplate humanity's place in the cosmos. Are we a cosmic accident, a solitary spark of consciousness in an endless, empty night? Or are we the precursors, the first fragile members of a future galactic community? The silence challenges our assumptions about the sustainability of intelligent life. It asks whether a species can navigate the treacherous waters between discovering fire and mastering atomic energy without self-immolating. This paradox has become a powerful driver of interdisciplinary research, blending the hard data of astronomy with the speculative models of biology, the long-term thinking of history, and the introspective nature of philosophy and sociology. It compels us to consider not just where the aliens are, but who we are and who we might become. The ongoing search for an answer, whether through radio telescopes, space-based observatories analyzing exoplanet atmospheres, or theoretical models of societal evolution, ensures that this great cosmic anomaly will continue to inspire wonder, humility, and a relentless curiosity about our lonely, and perhaps not so lonely, place in the universe. And then there was the signal that came and went in a single, breathtaking moment. An event so striking that it was immortalized not with a complex scientific designation, but with a single, heartfelt word written in red pen. Wow, it was August 15, 1977, at the Ohio State University's Big Ear radio telescope. This massive instrument was methodically scanning the sky as part of the search for extraterrestrial intelligence, or SETI, listening for any whisper that stood out from the natural radio hiss of the cosmos. On that quiet night, it heard something extraordinary. For 72 seconds, the telescope's receiver locked onto a powerful, narrowband signal emanating from the direction of the constellation Sagittarius. It wasn't the broad, messy static of a quasar or a pulsar. This signal was concentrated on one specific frequency, the hydrogen line at 1420 MHz, a frequency many scientists had theorized would be a logical choice for an interstellar beacon because it's a quiet, protected band in the radio spectrum where the universe's most common element naturally resonates. It was the exact kind of signal they were hoping to find, and its intensity shot up to 30 times louder than the background noise, creating a perfect, sharp peak on the old-fashioned computer printout. When volunteer astronomer Jerry Amon was reviewing the data a few days later, he was so stunned by its perfection that he circled the alphanumeric sequence and simply wrote "wow" in the margin. That single, spontaneous exclamation gave one of the most tantalizing mysteries in astronomy its name. The sheer quality of the "wow" signal is what has made it endure for decades as the best candidate for a potential alien transmission. It wasn't just loud, it was pristine. A signal from a natural cosmic source tends to be smeared across a range of frequencies, but this was a clean, narrowband burst, much like the kind produced by our own human technology. Furthermore, it exhibited the telltale sign of a celestial origin, because the Big Ear telescope used a fixed dish and relied on the Earth's rotation to scan the sky. Any genuine signal from a distant point in space would intensity for exactly 72 seconds as it passed through the telescope's beam, reach a peak, and then fade away, which is precisely the pattern the WOW signal displayed. It came, it peaked, and it vanished exactly as a signal from a fixed star system should. This wasn't a blip, it was a textbook example of what an intelligent, engineered signal from the cosmos was supposed to look like. The excitement was palpable, but it was immediately followed by the most frustrating part of the story. The Big Ear telescope and every other instrument pointed at that patch of sky for years afterwards listened intently, but the signal never, ever repeated. It was a one-time cosmic hello, a door that seemed to swing open for a moment, only to slam shut and leave us standing on the porch, wondering if we had imagined the whole thing. This enduring silence has forced scientists to search for other, more mundane explanations, though each one comes with its own set of problems. One of the most discussed natural explanations involved comets. In 2016, an astronomer proposed that the signal could have been caused by the hydrogen cloud surrounding two known comets that happened to be in that region of the sky at that exact time. Hydrogen can emit a strong radio signal, and the comets were in the right place. It was an elegant solution, but it quickly fell apart under scrutiny. Subsequent analysis revealed that these specific comets were not actually in the telescope's field of view on that August night, and more fundamentally, the hydrogen clouds around comets are diffuse and would produce a broad, weak signal, not the intense, narrowband spike that was recorded. Another common hypothesis is that it was a reflection, perhaps a piece of human space debris or even a secret military satellite, reflected a terrestrial radio transmission back down to Earth, creating a brief, deceptive echo. The problem, again, is the signal's properties. Our own television and radio broadcasts leak into space, but they are messy and broadband, not the pure, focused signal that was observed. To create such a signal from a reflection would require a highly unlikely and perfectly aligned series of events. After nearly 5 decades, no natural or human-made explanation has managed to fully account for all of the WOW signal's unique characteristics, which is why the possibility of an extraterrestrial origin, while unproven, has never been completely dismissed. The legacy of the WOW signal extends far beyond the mystery of its origin. It serves as a powerful and humbling lesson about the immense challenges of searching for intelligent life. The cosmos is vast, and transient events like this are, by their very nature, incredibly difficult to catch and verify. The Big Ear telescope, as advanced as it was for its time, could only look at one small point in the sky for a very short period. It had no way to instantly alert other observatories around the world to swing into action and confirm the detection. This single event highlighted a critical weakness in our strategy. The universe might not be broadcasting a continuous, easily findable beacon, but instead sending out brief, intermittent pulses. If you're not looking at the right place at the exact right moment, you will miss it forever. This realization has fundamentally shaped modern SETI. The search is no longer just about patience, it's about comprehensive, persistent coverage. The WOW signal anomaly is the ghost that haunts every new project, reminding engineers and astronomers of the absolute necessity for continuous, all-sky monitoring. This drive to never miss another WOW is the direct inspiration behind some of the most ambitious scientific endeavors in the world today. Projects like Breakthrough Listen, a decade-long, $100 million initiative, are the direct descendants of that single red pen circle. Using some of the world's most powerful radio telescopes, like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, Breakthrough Listen is systematically scanning the entire sky, the galactic plane, and the nearest 1 million stars. But it's not just about raw power, it's about intelligent searching. The project employs incredibly sophisticated algorithms and machine learning systems that can sift through millions of radio channels in real time, automatically filtering out human interference from satellites and cell phones and flagging any signal that has the hallmarks of being non-natural. They are building a system that, if a signal like the WOW event happened again today, would not only detect it instantly but would also trigger a global network of telescopes to immediately turn and stare at that location, seeking confirmation across multiple wavelengths and from multiple sites across the globe. The goal is to turn a one-time mystery into a verifiable, repeatable discovery. So, while we may never know for certain what caused that 72-second burst in 1977, its true value is undeniable. The WOW signal is a monument to the spirit of curiosity and the importance of persistence. It is a reminder that in a universe as vast and old as ours, the most profound messages might not be long, declarative speeches, but brief, enigmatic whispers. It teaches us that the search for cosmic companions is a marathon, not a sprint, requiring not just advanced technology but an enduring sense of wonder and a commitment to listening, night after night, year after year. That one word, WOW, scrawled on a piece of paper, continues to echo through the decades, a symbol of the thrilling possibility that we are not alone, and a challenge to keep listening for the next hello. But what if the universe itself has a hidden orientation, a subtle fingerprint of directionality that runs counter to everything we thought we knew? This brings us to one of the most philosophically unsettling anomalies in all of cosmology, a feature in the oldest light we can see that has earned the dramatic moniker, the axis of evil. To understand why this name is so fitting, we have to go back to the cosmic microwave background, that pristine afterglow from the dawn of time. According to our most cherished cosmological principles, this radiation should be isotropic. This means it should look fundamentally the same in every direction you look, a perfectly smooth and uniform tapestry of tiny temperature variations that were the seeds for all future galaxies. There should be no special axis, no preferred direction, no cosmic north. The universe, on its largest scales, is supposed to be a grand and featureless expanse. Yet, when scientists began creating exquisitely detailed maps of this background radiation, first with the WMAP satellite and later with the even more precise Planck mission, they noticed something that sent a ripple of disbelief through the community. The temperature fluctuations weren't completely random. They showed strange, large-scale alignments, a kind of pattern that seemed to whisper that the universe has a specific orientation, a preferred plane, an axis around which these primordial structures appear to be coordinated. It's as if you walked into a room that was supposed to be perfectly symmetrical, only to find that all the furniture was subtly angled toward one specific wall. This discovery strikes at the very foundation of modern cosmology, challenging the cosmological principle which has been a cornerstone of our thinking for over a century. This principle of uniformity and isotropy is not just a convenient assumption, it's the bedrock upon which we've built our entire understanding of the cosmos's evolution. It allows us to apply the same physical laws everywhere and to treat the universe as a homogeneous entity when modeling its history from the Big Bang to the present day. The axis of evil anomaly, if it proves to be real and not an illusion, would force us to reconsider this foundational pillar. Imagine trying to navigate using a compass that insisted on pointing toward one specific, unique direction in the universe, a direction that held some fundamental significance. It would mean our universe is not the same in all directions after all. that it has a kind of inherent spin or a primordial structure imprinted upon it from its very first moments. This is why the name Axis of Evil was coined, albeit with a touch of scientific dark humor. It's not that the axis is malevolent, but that its existence would be so disruptive to our standard models that it feels like a villain to our comfortable understanding of reality. Naturally, the first response from the scientific community was a deep and thorough search for a more mundane explanation. Could this be a colossal case of systematic error? Perhaps our own motion through space is creating a subtle distortion in the data. We know our solar system is moving relative to the rest frame of the cosmic microwave background, and this motion does create a detectable dipole effect, a kind of Doppler shift that makes one half of the sky appear slightly warmer and the other half slightly cooler. Scientists have meticulously subtracted this known effect, but the larger-scale alignments of the axis of evil seem to persist. Another possibility is that the anomaly is simply a statistical fluke. When you look at any complex set of data, you can sometimes find patterns that appear significant purely by chance, like seeing a face in the clouds. The universe is vast, and it's possible we are just seeing a rare, low-probability alignment that has no deeper meaning. However, as the data from Planck has gotten more and more precise, this fluke explanation has become increasingly difficult to sustain. The patterns are stubborn, and their statistical significance, while not yet at the gold standard 5 sigma level of a definitive discovery, is high enough to be deeply troubling and fascinating. This has prompted physicists to explore theories that venture into truly profound territory. Some have proposed modifications to the theory of inflation, the period of hyper-expansion in the universe's first fraction of a second. Perhaps the primordial quantum fluctuations that inflation stretched into the cosmic structures we see today were not perfectly Gaussian or random as we assume. Maybe they contained subtle correlations or patterns that have left this directional imprint on the entire cosmos. Other, even more radical ideas suggest that the axis of evil could be a relic from a time before the Big Bang, a scar from a pre-inflationary universe that had its own inherent structure. In this mind-bending scenario, our entire observable universe could be just one bubble in a vast multiverse, and the axis is a reflection of the larger, structured environment in which our bubble formed. It would be like a fossil embedded in the deepest layers of time, a clue to a reality that existed before our own began. The compelling and unsettling nature of this mystery is a powerful engine for scientific progress. The unresolved questions surrounding the axis of evil are directly driving the design and development of the next generation of cosmic microwave background experiments. Missions are being planned with even greater sensitivity and resolution, with the specific goal of hunting for the faint signatures of primordial gravitational waves, the so-called B-mode polarization. But these same advanced instruments will also be able to scrutinize the temperature fluctuations with an unprecedented level of detail, allowing scientists to determine once and for all if the axis is a real feature of the cosmos or a complex mirage born from a combination of subtle effects. They will test the fundamental symmetries of the universe with a precision we can barely imagine today, probing not just for the axis itself, but for any other deviation from the perfect isotropy we have long taken for granted. The quest to solve this puzzle is pushing the limits of our technology and our theoretical imagination, forcing us to consider possibilities that were once the realm of pure speculation. If this cosmic preference is confirmed, it would do more than just add a new fact to our textbooks. It would revolutionize our origin story, revealing that the universe was born with a built-in sense of direction, a hidden architecture that has been guiding the formation of everything we see from the very first moment. Now, let's shrink our perspective from the vast expanses of the cosmos down to the bizarre and counterintuitive world of the infinitesimally small, where a phenomenon so strange that even Albert Einstein called it spooky action at a distance might just hold the key to the universe's largest mysteries. This is quantum entanglement, a concept that defies our everyday intuition about how reality should work. Imagine you have a pair of magical dice. You take one die with you on a journey to a distant galaxy, leaving its twin back on Earth. The moment you roll your die and it lands on a 3, you know instantly, with absolute certainty, that the die back on Earth has also landed on a 3. This connection seems to happen faster than the speed of light, a notion that made Einstein deeply uncomfortable, as it appeared to violate the fundamental cosmic speed limit set by his own theory of relativity. In the quantum world, this is exactly what happens with particles like electrons or photons. When two particles become entangled, they lose their individual identities and are described by a single, shared quantum state. No matter how far apart you separate them, whether it's across a lab bench or across the observable universe measuring the property of one particle, like its spin or polarization, will immediately and irrevocably determine the property of the other. This connection is instantaneous and seemingly ignores the distance between them, creating a profound link that has been verified in countless experiments, confirming that our classical, common-sense view of a local and separable reality is fundamentally incomplete. For decades, entanglement was seen as a fascinating, if somewhat peculiar, feature of the microscopic world, a party trick for physicists to demonstrate the weirdness of quantum mechanics. But in recent years, a revolutionary idea has begun to take hold, one that suggests this spookiness isn't just a small-scale curiosity. It might be the very glue that holds the fabric of spacetime together. This breathtaking connection between the tiny quantum world and the grand cosmic stage is emerging from the study of some of the most intractable problems in physics, particularly the black hole information paradox. As we discussed earlier, this paradox pits quantum mechanics against general relativity, questioning what happens to information that falls into a black hole. The resolution proposed by physicists like Juan Maldacena and Leonard Susskind points directly to entanglement. Their work on the holographic principle suggests that all the information describing a volume of space, like the interior of a black hole, might actually be encoded on its two-dimensional boundary, its event horizon, much like a three-dimensional hologram is stored on a flat, two-dimensional surface. And what is the mechanism that creates this incredible connection between the boundary and the interior? The leading candidate is quantum entanglement. The particles on the surface are thought to be wildly entangled with the particles inside, weaving the very geometry of spacetime through their interconnected quantum states. This line of thinking has led to one of the most elegant and profound conjectures in modern theoretical physics, known as AR equals EPR. This deceptively simple equation connects two ideas that were once thought to be completely separate. On one side, ER refers to an Einstein-Rosen bridge, which is the formal name for a wormhole, a hypothetical tunnel through spacetime that could connect two distant points. On the other side, EPR stands for Einstein, Podolsky, and Rosen, the physicists who first highlighted the spooky nature of quantum entanglement in a famous paper. The ER equals EPR proposal, largely championed by Susskind, suggests that these two concepts are not just analogous, they are two different descriptions of the same underlying reality. It posits that every pair of entangled particles is, in fact, connected by a microscopic wormhole. This isn't a wormhole you could travel through. It's unimaginably tiny, existing at the Planck scale. But the implication is staggering. It means that the mysterious, instantaneous connection of entanglement isn't a ghostly signal flying through space. It's a direct link through the geometry of spacetime itself. The particles aren't communicating, they are simply two ends of the same cosmic thread, intimately connected by a shortcut through the fabric of the universe. This idea provides a potential geometric foundation for quantum mechanics, suggesting that the weird interconnectedness of the quantum world is a direct manifestation of the architecture of spacetime. If entanglement is indeed the fundamental ingredient from which spacetime is woven, then it opens up incredible new ways to probe the cosmos, turning the entire universe into a giant quantum computer whose connections we can potentially decipher. One of the most exciting cosmic applications involves using the pattern of entanglement to peer back into the earliest moments of the universe. The cosmic microwave background, that fossilized light from the Big Bang, contains tiny temperature fluctuations that are the seeds of all cosmic structure. Theorists are now asking if the specific patterns we see in this ancient light could be a reflection of the quantum entanglement that existed between different patches of the primordial universe. The way these patches are correlated across the sky might be a direct map of the universe's initial quantum connections, frozen in time and stretched across the cosmos by inflation. Furthermore, this perspective offers a radical new way to think about the universe's accelerating expansion. The enigmatic dark energy which drives this acceleration could be understood not as a mysterious substance, but as a consequence of the changing entanglement structure of the cosmic vacuum. As the universe expands, the sheer volume of space increases, and with it, the total number of potential quantum connections. Some theories suggest that this evolving web of entanglement itself generates the repulsive force we call dark energy, providing a potential bridge between the quantum world and one of cosmology's greatest puzzles. To test these extraordinary ideas, we cannot rely on theory alone. We must push our experimental capabilities to the absolute limit, and that is precisely what is happening right now in labs and in space. While entanglement has been confirmed over distances of hundreds of kilometers on Earth, scientists are now taking this research into orbit. Missions like China's Mission's quantum satellite have successfully demonstrated entanglement between photons separated by over 1,000 kilometers, beaming their linked states down to ground stations on Earth. These experiments are crucial for two reasons. First, they rule out any potential loopholes by ensuring the particles are so far apart that no hidden signal could possibly travel between them at the speed of light in the time it takes to make a measurement. Second, and perhaps more importantly, they are the first steps toward building a future quantum internet and developing space-based tests of fundamental physics. These satellites are proving that entanglement, this seemingly fragile quantum link, can survive the harsh journey through Earth's atmosphere and the vacuum of space, paving the way for experiments that could one day use entangled particles to probe the nature of gravity itself and test whether the entanglement of particles is affected by the curvature of spacetime, as some theories of quantum gravity predict. This grand synthesis where the spooky action of tiny particles becomes the architect of cosmic reality represents the bleeding edge of theoretical physics. The quest to understand how entanglement underpins spacetime is a central driving force in the search for a theory of quantum gravity, the long-sought framework that would finally unite Einstein's general relativity with the quantum mechanics of the subatomic world. For decades, these two pillars of modern physics have been fundamentally incompatible, with one describing the force of gravity as the curvature of a smooth, continuous spacetime, and the other describing a microscopic world of discrete, probabilistic events. Entanglement provides a potential common language. If spacetime itself is an emergent property of a vast network of entangled quantum bits, or qubits, then gravity is no longer a fundamental force, but a consequence of the quantum information structure of the universe. This vision inspires approaches like string theory and loop quantum gravity, which, in their own ways, attempt to describe how the seamless geometry of spacetime arises from the discrete, interconnected quantum foundations. The phenomenon of entanglement demonstrates with stunning clarity that the smallest scales and the largest scales are not separate realms. The key to unlocking the universe's grandest cosmic puzzles, from the fate of black holes to the origin of everything, may very well lie in understanding the mysterious, instantaneous, and profound connections that bind the quantum world together. Imagine the ultimate cosmic shredder, a place so powerful that it can swallow entire stars and crush them into a fundamental nothingness. This is the promise of a black hole according to Einstein's general relativity. Once something crosses the event horizon, that point of no return, it is gone forever, lost to the universe, its identity erased by an infinitely dense point called a singularity. The black hole, in this view, is the universe's ultimate eraser. But then there is quantum mechanics, the wildly successful set of rules that governs the microscopic world. And quantum mechanics has a fundamental, unbreakable law: information cannot be destroyed. Information, in this sense, is not just data on a hard drive. It is the unique identity of every particle, its spin, its charge, its type. The quantum state of every atom that made up a star, every molecule that formed a planet, must, in principle, be preserved. Even if you burn a book, the information in its letters is not truly lost. It is just chaotically scrambled into the smoke and heat. In theory, with a perfect understanding of physics, you could reverse the process and reconstruct the book from its ashes. But what happens when you throw the book into a black hole? General relativity says it is obliterated, its information permanently deleted at the singularity. Quantum mechanics says that is absolutely impossible. This is the black hole information paradox, a direct and furious clash between our two most powerful descriptions of reality, and for decades it has represented the single greatest crisis in theoretical physics. The heart of the problem was sharpened to a fine point by Stephen Hawking in the 1970s. He discovered that black holes are not completely black. Due to weird quantum effects happening just outside the event horizon, they slowly leak a faint glow of particles, now known as Hawking radiation. This radiation causes the black hole to gradually lose mass, shrinking over unimaginable eons until it presumably evaporates completely and vanishes. Here's the catastrophic catch. Hawking calculated that this radiation is purely thermal. It is random, featureless heat like the glow from a furnace. It carries no information whatsoever about what fell into the black hole. So, if the black hole eventually evaporates into a cloud of this random radiation, what happened to the information of all the things it consumed? According to this calculation, the information is truly, irrevocably lost, violating a sacred principle of quantum mechanics. This left physicists with a horrifying choice. Either quantum mechanics is wrong, which would dismantle the foundation of all modern particle physics, or general relativity is wrong, which would overthrow our understanding of gravity, space, and time. It seemed you could have one set of laws or the other, but not both. This impossible dilemma forced physicists to propose some truly bizarre solutions. One of the most dramatic ideas is the concept of a firewall. Imagine that the event horizon is not a peaceful boundary you could cross without noticing, as general relativity suggests. Instead, it is a searing wall of energetic particles, a cosmic shredder that instantly incinerates anything that touches it. In this scenario, information is not lost inside the black hole. It is destroyed right at the door. The firewall would resolve the paradox by saving quantum mechanics. but at the cost of radically violating Einstein's principle of equivalence, which states that an observer falling into a black hole should not experience anything unusual at the event horizon. It's a solution that feels almost like a desperate act, trading one set of physical laws for another, and it highlights just how deep the conflict runs. Fortunately, a more elegant and revolutionary path has emerged from the frontiers of string theory and a concept known as holography. The holographic principle is a mind-bending idea that suggests our perception of a three-dimensional universe might be an illusion. It proposes that all the information needed to describe a volume of space like the interior of a black hole can be entirely encoded on its two-dimensional boundary, its event horizon. Think of it like a security hologram on your credit card. The image has a three-dimensional appearance, but all its information is stored on the flat, two-dimensional surface of the card. In the same way, the holographic principle suggests that every particle, every bit of energy that falls into a black hole, does not travel down to a singularity. Instead, its information is immediately smeared out and stored as a kind of quantum code on the surface area of the event horizon. The black hole's interior, in this view, is a projection, a holographic illusion built from the data written on its surface. This leads to a breathtaking resolution of the paradox. When Hawking radiation is emitted, it doesn't just randomly pop out of the vacuum. The radiation particles are subtly entangled with the information encoded on the event horizon. As the black hole evaporates, this information is not lost. It is slowly and meticulously transferred to the outgoing radiation. It is an incredibly complex and chaotic process, like burning an entire library and having the unique identity of every book somehow imprinted into the pattern of the light and heat from the flames. To an outside observer, the radiation would initially look random, but with a complete understanding of the quantum code, one could, in principle, decode the radiation and reconstruct everything that ever fell into the black hole. The information was never truly inside the black hole. It was always on the surface, and it is faithfully returned to the universe, preserving the sacred rule of quantum mechanics. The implications of this resolution ripple far beyond the theoretical, reaching into the very real and emerging field of gravitational wave astronomy. When two black holes collide, they create ripples in spacetime that we can now detect with instruments like LIGO and Virgo. The information paradox and its holographic resolution suggest that the event horizons of these black holes are not featureless membranes. They are dynamic information encoding surfaces, the specific way they vibrate and settle down after a collision. The ringing that we detect in the gravitational wave signal could potentially carry the signature of this quantum information. Future, more sensitive detectors might one day be able to see the faint imprints of these quantum effects, turning the violent crashes of black holes into cosmic laboratories for testing the ideas of holography and the ultimate fate of information. Ultimately, the black hole information paradox is far more than an abstract puzzle. It is a powerful engine driving us toward a deeper unity in physics. It forces us to confront the fact that our current theories, however successful, are incomplete. The paradox shows us that black holes are not merely exotic graves for stars. They are the ultimate testing grounds, the places where the laws of quantum mechanics and gravity meet and must be reconciled. The decades-long struggle to resolve it has not just given us potential answers. It has fundamentally reshaped our understanding of space, time, and information itself, revealing a universe that is far more interconnected, holographic, and wondrous than we ever imagined. While our galaxy is tugged by the Great Attractor and our solar system's edge is marked by the Kuiper Cliff, a single, unassuming star over 1,000 light-years away has captivated the world by doing something remarkably simple: it keeps flickering. Known officially as KIC 8462852, but immortalized as Tabby's star after its principal investigator Tabetha Boyajian, this star behaves like no other we have ever seen. Nestled in the constellation Cygnus, it was the Kepler Space Telescope that first uncovered its bizarre nature, revealing a pattern of dimming so extreme and irregular that it defies all conventional explanation. Imagine watching a distant light bulb. Normally, if a planet passes in front of it, the bulb's light would dim by perhaps 1% for a few hours in a perfectly predictable, rhythmic pattern. Now imagine that same light bulb suddenly dimming by a staggering 22%, as if a vast, jagged shape drifted past and then returning to normal, only to dim again months or years later in a completely different, unpredictable way. This is the profound anomaly of Tabby's star. Its light curve is a chaotic scribble of deep, aperiodic dips, some lasting for days, others for weeks, with no discernible pattern. A single one of these events could be explained away, but the repeated, dramatic nature of the dimming points to an object, or more likely a collection of objects, of absolutely immense scale orbiting the star, blocking its light in a way that simply should not be possible for any natural system we understand. The sheer extremity of the signal immediately ignited the most thrilling of all possible explanations. Could this be evidence of an alien megastructure? The concept, first proposed by physicist Freeman Dyson, imagines a civilization so advanced that it constructs a vast swarm of energy-collecting panels orbiting its host star, a Dyson sphere, to harness nearly all of its stellar output. Such a colossal engineering project would not be a solid shell, but a messy, uneven network of collectors and habitats, which would perfectly account for the irregular, deep, and non-repeating dimming patterns we observe. The idea captured the public imagination like few other scientific discoveries, turning a technical data plot into a global sensation. It was a hypothesis that was both terrifying and exhilarating, forcing us to confront the possibility that we were not just looking at a star, but at the works of an intelligence capable of rearranging its entire solar system. While the scientific community remained rightly skeptical, the alien megastructure theory served a vital purpose. It pushed astronomers to think bigger and to consider every conceivable natural explanation with even greater rigor, because to prove it was aliens, you first have to rule out every single natural phenomenon, and that has proven to be a monumental challenge. Primary natural suspect was a vast, fragmented swarm of comets. The idea was that a family of exocomets, perhaps disturbed by a passing star, could be on long, eccentric orbits around Tabby's star. As they approached the star, they would break up, releasing enormous clouds of dust and debris that could occlude its light in the irregular, deep fashion observed. This was a compelling idea, as cometary dust is excellent at blocking light. However, when astronomers turned the Spitzer Space Telescope, which sees in infrared light, towards Tabby's star, they hit a major snag. Dust like that from comets absorbs starlight and re-radiates it as heat in the infrared. If a massive cloud of fine dust were causing the 22% dimming, Spitzer should have detected a significant brightening in the infrared. It did not. The lack of excess infrared heat was a heavy blow to the simple comet swarm model, suggesting that whatever is blocking the light is not made of small, warm dust grains, but is likely composed of larger, opaque objects that do not radiate much heat. This forced a refinement of the hypothesis, suggesting the material could be made of larger, colder fragments, but the puzzle only deepened. Other astronomers looked not outwards at orbiting material, but inwards at the star itself. Could the dimming be caused by the star's own internal processes? Some stars are known to be variable, changing in brightness due to pulsations or giant starspots. But Tabby's star is a fairly ordinary main sequence star, slightly larger and hotter than our Sun, and its type of star is not known for such extreme variability. The dips are far too deep and asymmetrical to be caused by pulsations, and to create a 22% dimming with star spots would require nearly half the star's surface to be covered in spots, a phenomenon never observed in a star like this. Furthermore, long-term studies of historical photographic plates revealed another shocking layer to the mystery. Analysis of century-old data suggested that Tabby's star has also been undergoing a long-term, secular dimming, fading by as much as 14% over the past 100 years. This gradual fading on top of the sharp dips is even more difficult to explain, as it would require a mind-boggling amount of material to have passed in front of the star over a century, far more than any known cometary family or debris disk could provide. Each proposed natural explanation seems to solve one piece of the puzzle while creating another, leaving the star's behavior as enigmatic as ever. This ongoing cosmic detective story has had a transformative impact on how astronomy is done, breaking down the walls of the ivory tower and inviting the world to participate. The initial discovery of Tabby's star's bizarre behavior was not made by a professional astronomer sifting through data, but by citizen scientists, volunteers in the Planet Hunters project who were examining Kepler's light curves from their home computers. It was their sharp eyes that flagged this star as "what the heck is this?" and brought it to the attention of Dr. Baryon and her team. This public engagement exploded when the star hit the headlines. In a stunning display of collective interest, over 1,700 people contributed more than $100,000 through a Kickstarter campaign to secure dedicated time on a global network of ground-based telescopes to monitor the star continuously. This crowd-funded effort ensured that the next time Tabby's star decided to act strangely, the world was watching, capturing valuable data that would have otherwise been missed. This anomaly single-handedly popularized the concept of automated, all-sky monitoring for stellar anomalies, proving that the public is not just a passive audience, but an active and crucial partner in the scientific process. The legacy of Tabby's star, therefore, extends far beyond its own mysterious flickers. It stands as a powerful testament to the importance of open-mindedness and interdisciplinary collaboration in science. This one star has drawn in stellar astrophysicists, planetary scientists, dynamicists, and even those who ponder the possibilities of life in the universe. It forces experts in these different fields to talk to one another, to combine their knowledge to attack a problem that resists a simple classification. Is it a star problem, a planetary system problem, or something else entirely? Tabby's star exemplifies how a single, stubborn piece of anomalous data can act as a catalyst, shaking multiple scientific disciplines out of their comfort zones and pushing them to develop new models and new observing strategies. It teaches us that the most exciting phrase in science is not "Eureka," but "that's funny." It encourages a healthy balance of rigorous skepticism and boundless curiosity, reminding us that the universe is under no obligation to conform to our expectations, and that the greatest discoveries often begin with a single, inexplicable flicker in the night. Then, in 2017, our solar system received its first confirmed tourist from a distant star. A strange, swift object was detected hurtling past the Sun, and its trajectory made it undeniably clear this traveler was not from here. Named Oumuamua, a Hawaiian word meaning scout from the distant past, it was the first interstellar object ever observed within our own cosmic neighborhood. Immediately, it stood out as profoundly alien. For starters, its shape was unlike anything in our solar system. Based on the way its brightness fluctuated dramatically as it tumbled through space, astronomers deduced it was highly elongated, perhaps 10 times as long as it was wide, resembling a cosmic pancake or a cigar. This was bizarre, as most asteroids and comets we see are at least somewhat roundish. But the real head-scratcher came when scientists tracked its path with extreme precision. As Oumuamua sped away from the Sun, it wasn't just coasting under gravity's influence alone. Something was giving it an extra, tiny push, a non-gravitational acceleration that gently altered its trajectory. This is a behavior often seen in comets, where sunlight vaporizes subsurface ices, and the resulting jets of gas act like tiny rocket engines. The catch: Oumuamua showed no visible signs of this activity, no surrounding cloud of gas and dust, no tail streaming behind it. It was accelerating in complete, unnerving silence. This combination of a bizarre shape and a hidden engine set off a firestorm of scientific debate and public fascination. How do you explain an object that moves like a comet but looks like an asteroid and acts like neither? The scientific community scrambled to propose natural explanations that could fit all the strange data. One of the most creative ideas was that Oumuamua might be a hydrogen iceberg. In the cold, dense cores of giant molecular clouds, it's theorized that frozen hydrogen could accumulate, forming solid bodies. As such an iceberg neared the Sun, the theory went, the solar radiation would cause the solid hydrogen to sublimate directly into gas, providing the thrust for the observed acceleration without producing any visible dust. Hydrogen is invisible to our telescopes. It was an elegant solution, but it had a major flaw. The interstellar medium is a harsh environment bathed in cosmic radiation. A fragile hydrogen iceberg would likely have been eroded away long before it ever reached our solar system, making its journey statistically improbable. A more widely accepted natural hypothesis involves outgassing from water ice. Perhaps Oumuamua was a very old, very rocky comet whose volatile ices were largely depleted. When it passed close to the Sun, the remaining water ice deep within its body could have turned to gas, escaping through porous channels in the rock without dragging much dust with it. This would explain the push without the classic cometary coma, but it still struggles to fully account for the object's extreme shape and the precise nature of its acceleration. Of course, the most tantalizing and controversial hypothesis came from Harvard astronomer Avi Loeb, who suggested we should at least consider the possibility that Oumuamua was not a natural object at all, but a piece of advanced alien technology. Specifically, he proposed it could be a light sail, a vast, thin sheet designed to be pushed by the radiation pressure from starlight, much like a boat's sail is pushed by the wind. This would naturally explain its flattened shape and its non-gravitational acceleration without any need for visible outgassing. The idea captured the global imagination, but the vast majority of the scientific community remains deeply skeptical. They argue that while the light sail idea is provocative, it is not yet necessary. The history of astronomy is filled with mysteries that were eventually explained by natural, if unexpected, phenomena without invoking extraterrestrial intelligence. Occam's razor, the principle that the simplest solution is often the best, suggests we should exhaust all natural explanations first. The debate, however heated, was scientifically productive. It forced everyone to sharpen their arguments, to scrutinize the data more carefully, and to acknowledge that our current categories for comet and asteroid might be too simplistic for objects born around other stars. The true, lasting legacy of Oumuamua is not in the specific answer to what it was, but in the profound questions it raised about the population of interstellar objects. Its detection by the Pan-STARRS telescope in Hawaii was a matter of sheer luck. It was already on its way out of the solar system by the time we spotted it. This implies that there must be a vast number of similar objects passing through our solar system undetected. Oumuamua's anomalous behavior challenges our standard models of how minor bodies behave, suggesting that the processes of planetary formation in other star systems can create objects with properties we have never seen before. Are there more pancake-shaped objects out there? Are there more dark, stealthy comets that accelerate without a trace? The only way to find out is to be better prepared, and Oumuamua has served as a cosmic wake-up call, jolting the world's space agencies into action. The European Space Agency, for instance, has fast-tracked its Comet Interceptor mission, designed to park a spacecraft in a holding position, ready to be dispatched at a moment's notice to rendezvous with the next intriguing interstellar visitor or a pristine comet from our own outer solar system. The goal is to have a spacecraft capable of meeting one of these objects while it is still relatively close, allowing for a close-up analysis that could finally provide definitive answers. This new urgency underscores a critical need for rapid response observational protocols and unprecedented international collaboration. The next Oumuamua could be discovered tomorrow, and it will be a fleeting opportunity. We need a global network of telescopes, both on the ground and in space, that can instantly swing into action to track an incoming object, measuring its rotation, its composition, and its trajectory with incredible precision from the moment it's found. This requires pre-approved observing time, shared data agreements between countries, and the logistical framework to coordinate a worldwide observing campaign in a matter of days or even hours. The mystery of our first interstellar scout has fundamentally changed our perspective, transforming our solar system from an isolated island into a bustling crossroads in a dynamic galactic environment. We now understand that pieces of other planetary systems are constantly sailing past us, each one a potential messenger carrying secrets about how worlds are built around other suns. Oumuamua, in its silent, enigmatic passage, taught us that we live in a galaxy that is far more interconnected and filled with far more variety than we ever dreamed, and it has equipped us with a new sense of purpose to be better watchmen at the shore, ready to greet the next strange traveler from the cosmic ocean. Tucked away within the most perfect baby picture of the universe, the cosmic microwave background, lies a feature so bizarre it feels like a cosmological prank. Known as the cold spot, this large, unusually frigid region in the sky is far more than just a random chill in the cosmic afterglow. It stands out as a significant and persistent anomaly, a place where the temperature of the primordial light is markedly lower than the models predict. For years, the most straightforward explanation for such a cold patch was the idea of a cosmic supervoid. Imagine the universe as a vast, three-dimensional web, with galaxies clustered along dense filaments and enormous, empty bubbles in between. A supervoid is one of these bubbles, a region of space that is largely empty, containing far fewer galaxies and much less matter than the cosmic average. According to the principles of general relativity, when light travels through such an underdense region, it loses a tiny amount of energy climbing out of the shallower gravitational well. This effect, known as the integrated Sachs-Wolf effect, would cause the cosmic microwave background radiation passing through the void to appear slightly colder to us. It's a clean, elegant explanation that fits neatly within our standard understanding of cosmology. The hunt was on to find the supervoid that must be causing this cosmic cold spot. Astronomers pointed their most powerful telescopes toward the direction of the cold spot, meticulously counting galaxies and mapping the large-scale structure in that part of the universe. And they did, in fact, find a void. Surveys revealed a significant underdensity of galaxies, a vast and mostly empty region of space that seems to align with the cold spot's location. This discovery was initially encouraging, seeming to confirm the supervoid hypothesis. However, a major problem quickly emerged when scientists did the math, calculating how much of a temperature drop this specific void should cause. The numbers didn't add up. The observed void is indeed large, but it is not nearly large enough or empty enough to account for the profound coldness we see in the cosmic microwave background. The actual temperature dip is about 70 microkelvins colder than the surrounding areas, while the void can only explain a small fraction of that cooling. This discrepancy is the heart of the mystery. We have found the suspect, but it doesn't seem to have the strength to have committed the crime. The evidence is there, but it's insufficient, leaving a glaring gap in our understanding and opening the door to far more exotic and thrilling possibilities. With a simple supervoid explanation falling short, cosmologists have been forced to consider ideas that sound like they are pulled from the pages of a science fiction novel. One of the most mind-bending proposals is that the cold spot is not a lack of something, but the imprint of a cosmic collision. This theory suggests that our universe might have bumped into another universe in the distant past, a concept that arises naturally from certain models of the multiverse and eternal inflation. In this scenario, the cold spot could be a kind of cosmic bruise, a remnant of an energy exchange that occurred when our bubble universe grazed another. The physics of such an event would create a specific signature in the cosmic microwave background, and the cold spot's properties bear a striking resemblance to what those models predict. It's a breathtaking thought that we might be looking at direct evidence of a parallel universe, a scar left from a primordial encounter that forever marked the fabric of our own cosmos. While this is an incredibly speculative idea, it demonstrates the lengths to which scientists are willing to go to explain this persistent anomaly, pushing the boundaries of what is considered testable physics. Another compelling, though equally exotic, explanation involves a concept known as a cosmic texture. In the frenzied, high-energy moments following the Big Bang, the fundamental fields that make up our universe were undergoing rapid phase transitions, much like water freezing into ice. Sometimes these transitions could have been imperfect, creating knots of concentrated energy known as topological defects. A cosmic texture is one such defect, a kind of tangled knot in the very fabric of spacetime. If one of these textures formed and then unraveled in the early universe, it would have released a tremendous amount of energy, creating a spherical shockwave that would leave a specific, cold imprint on the cosmic microwave background. The cold spot matches the predicted size and temperature profile of such an event almost perfectly. This explanation doesn't require other universes, but it does require physics beyond our current standard model, pointing to grand unified theories that attempt to describe the forces of nature when they were all one. Whether it's a collision with another universe or the unraveling of a cosmic knot, these theories show how a single anomaly can force us to confront the most fundamental questions about the origin and structure of everything. This profound mystery is not just a theoretical playground. It is a powerful driving force behind some of the most ambitious observational campaigns in modern astronomy. The James Webb Space Telescope, with its unparalleled infrared vision, is not just looking at the first galaxies. It is also being used to conduct deep field surveys precisely in the direction of the cold spot. The goal is to create a census of galaxies in that region with a level of detail never before possible, to see if there is a previously undetected, even larger underdensity of galaxies that could explain the temperature drop. Perhaps the void is part of a nested structure of emptiness, a supervoid within a supervoid that our previous telescopes simply could not resolve. At the same time, next-generation cosmic microwave background experiments are being designed with the cold spot specifically in mind. These incredibly sensitive telescopes will scan the sky, measuring the polarization and temperature of the ancient light with microscopic precision, searching for the unique swirls and patterns that would be the smoking gun for a cosmic texture or the specific signature of a bubble collision. The cold spot has become a cosmological touchstone, a testbed for our most fundamental theories about the universe's explosive birth and its potentially infinite expanse. Ultimately, the story of the cold spot is a perfect illustration of how science grapples with the unknown. It began with a simple, elegant hypothesis, a supervoid that seemed to fit our standard model. When the data refused to fully cooperate, it didn't mean the end of the inquiry. It meant the beginning of a much deeper and more fascinating investigation. This single cold patch on the sky is more than just a data point. It is a keyhole. It is a tiny window through which we can potentially peer into the pre-inflationary universe, a time before the rapid expansion that shaped our cosmos began. It challenges the inflationary paradigm itself, suggesting that the initial conditions of the universe might have been more complex and structured than we ever imagined. Whether the final answer is a subtle statistical fluke, a complex void we have yet to fully map, or evidence for a multiverse, the journey to understand the cold spot has already reshaped cosmology. It reminds us that the universe is under no obligation to be simple, and that its greatest secrets are often hidden in its most subtle and perplexing features. While our gaze has been drawn to the flickers of distant stars and the cold spots on the edge of time, one of the most compelling mysteries is radiating from the very heart of our own cosmic home. If you could see the sky with gamma-ray eyes, the center of our Milky Way galaxy would not be a place of darkness, but a roiling, brilliant cauldron of light. This is the most energetic form of light in the universe, and it pours out from the galactic core in a constant, furious stream. For years, astronomers have known that much of this gamma-ray glow comes from familiar, if extreme, sources. You have the violent final breaths of massive stars in supernova remnants, which accelerate particles to nearly the speed of light. You have pulsars, the lighthouses of the cosmos, spinning madly and beaming out radiation. And you have cosmic rays, high-energy protons and atomic nuclei, slamming into interstellar gas and producing gamma rays as a byproduct of their collisions. Yet, when scientists at the helm of the Fermi Gamma Ray Space Telescope began to meticulously map this radiation, they found something that didn't belong. After they carefully subtracted the expected glow from all these known sources, a persistent residual excess of gamma rays remained, hovering around the galactic center like a ghostly, energetic halo. This is the galactic center excess, and its presence signals that something powerful and unseen is at work in the dense core of our galaxy. The most thrilling possibility, the one that sends a jolt of excitement through the particle physics community, is that we are witnessing the indirect signature of dark matter itself. The leading theoretical candidates for dark matter, particles known as weakly interacting massive particles or WIMP, carry a fascinating property. They are theorized to be their own antimatter counterparts. This means that when two WIMP collide, they can annihilate each other, converting their entire mass into pure energy in accordance with Einstein's famous equation, E equals mc squared. This annihilation would produce a cascade of standard model particles, which would then rapidly decay into a shower of secondary products, including gamma rays. The distribution of this observed excess is particularly tantalizing. It isn't a single, pinpoint source like a star would be. Instead, it's a smooth, broadly distributed glow that extends for thousands of light years from the galactic center. This is exactly what many dark matter models predict. We believe our galaxy is embedded within a vast, roughly spherical halo of dark matter, and that halo is densest at its center, just like the excess. The gamma-ray signal appears to trace out the invisible architecture of this dark matter halo, as if we are finally seeing the outline of the universe's most elusive substance. Yet, in science, extraordinary claims require the rigorous elimination of all ordinary explanations, and the galactic center is nothing if not an extraordinary place. The primary astrophysical challenger to the dark matter hypothesis is a hidden population of millisecond pulsars. These are ancient neutron stars that have been spun up to incredible speeds by siphoning material from a companion star. They rotate hundreds of times per second, and in doing so, they can become incredibly efficient factories for gamma rays. The central bulge of our galaxy is a stellar metropolis, packed with ancient stars, and it is precisely the kind of environment where vast numbers of these millisecond pulsars could have formed. Individually, they would be too faint and too numerous for Fermi to resolve as distinct points of light. Collectively, their combined, unresolved glow could perfectly mimic the smooth, extended signal we attribute to the excess. It's a classic scientific puzzle. Are we seeing the collective signal of a known but unseen population of celestial objects, or are we seeing the first faint glow of a particle that has never been directly detected? This is not a debate that can be settled by looking at gamma rays alone. To separate these two competing visions of the galactic core, astronomers have had to become cosmic detectives, pulling in evidence from across the entire electromagnetic spectrum. They turn to powerful radio telescopes, like the Very Large Array, to search for the faint, telltale radio pulses that would unmistakably identify individual millisecond pulsars within the haze of the excess. They use infrared observatories like the Spitzer Space Telescope to map the distribution of ancient stars in the galactic bulge, creating a stellar census to see if the number of potential pulsar progenitors aligns with the strength of the gamma-ray signal. The key is correlation. If the gamma-ray excess perfectly traces the distribution of ancient stars, the case for pulsars grows stronger. If, however, it more closely matches the predicted profile of a smooth dark matter halo, then the particle physics explanation gains significant weight. The current data presents a frustrating and fascinating ambiguity. It seems to sit right on the fence with aspects that support both interpretations, keeping the mystery alive and the scientific community vigorously engaged. This unresolved debate is far more than an academic exercise. It is actively driving innovation in the way we search for dark matter. The hunt has traditionally focused on two other methods, creating dark matter in particle colliders like the Large Hadron Collider, or detecting it directly as it passes through ultra-sensitive, deep underground detectors. The galactic center excess represents a powerful third front, indirect detection. We are not trying to make it or catch it, but to observe the aftermath of its natural interactions in space. The ongoing analysis of this anomaly has pushed scientists to develop increasingly sophisticated statistical tools and computer models to sift through the Fermi data, separating potential dark matter signals from the complex astrophysical foregrounds. Furthermore, it has motivated a new kind of comparative astronomy. If this signal is truly from dark matter annihilations, then it shouldn't be unique to the Milky Way. Dwarf spheroidal galaxies, small, faint satellites of our own galaxy, are believed to be dominated by dark matter and contain very few of the conventional astrophysical sources that could produce gamma rays. They are pristine laboratories. The fact that Fermi has not detected a strong, similar gamma ray excess from most of these dwarf galaxies is a point against the dark matter interpretation. But researchers continue to scrutinize them, knowing that a single, clear detection could break the case wide open. The story of the galactic center excess is a perfect microcosm of modern astrophysics. showcasing the essential and sometimes tense partnership between particle physicists and traditional astronomers. For a particle physicist, the signal is a clean laboratory, a potential window into new laws of physics beyond the standard model. They can tweak the proposed mass and interaction strength of their hypothetical WIMP to perfectly fit the gamma-ray data. For an astronomer, the galaxy is a messy, complex system, and the null hypothesis must always be that we are seeing a new type of astrophysical source or a collective phenomenon we don't yet fully understand. This tension is not a weakness, it is the engine of progress. It forces both sides to sharpen their arguments, to improve their models, and to seek out ever more creative ways to test their ideas. The mystery exemplifies the power of multi-wavelength astronomy, proving that to understand the universe at its most extreme, you cannot rely on a single type of light. You need to combine the high-energy vision of gamma-ray telescopes with the detailed stellar maps from infrared surveys and the precise timing of radio observatories. This collaborative, multi-pronged attack on a single anomaly is pushing the boundaries of an entire field, demonstrating that whether the final answer points to pulsars or particles, the journey to find it is fundamentally expanding our understanding of the hidden forces at work in the heart of our galaxy. Now, let's travel back to the universe's very first minutes, a time of almost unimaginable heat and density when the cosmos was a seething nuclear furnace forging the very first atomic nuclei. This process, known as Big Bang nucleosynthesis, produced the primordial ingredients for everything that would follow: vast amounts of hydrogen and helium, and trace quantities of a few other light elements, including lithium. For the most part, our theoretical predictions for these primordial abundances line up beautifully with what astronomers actually observe in the oldest corners of the universe. But there is one glaring, persistent exception. When it comes to lithium, the numbers simply do not add up. The amount of lithium-7 we actually detect in ancient stars is only about 1/3 of what our most sophisticated models of the Big Bang insist should be there. This isn't a minor rounding error. It is a factor of 3 discrepancy that has stubbornly resisted explanation for decades. This is the lithium problem, a quiet but profound crack in the otherwise resoundingly successful story of the Big Bang, reminding us that even our most well-established cosmic models still hold fascinating secrets. To grasp why this shortfall is so puzzling, it helps to understand the incredible precision of Big Bang nucleosynthesis. The theory provides a remarkably detailed recipe for the universe's first elements. In the first few minutes after the Big Bang, the entire cosmos was hot and dense enough for nuclear reactions to occur everywhere at once. Protons and neutrons collided and fused, first forming deuterium, then helium, and finally, a tiny trace amount of lithium-7, the most common stable isotope of that element. The calculations that predict these abundances are not rough guesses. They are precise outcomes that depend on known nuclear physics and the conditions of the early universe, such as the density of ordinary matter and the expansion rate. The predicted abundances for deuterium and helium-4 match the observations with stunning accuracy, which gives us tremendous confidence in the overall model. This makes the lithium discrepancy all the more jarring. It's as if you followed a famous cake recipe to the letter, and the cake turned out perfectly, except that one key ingredient, the vanilla, was present at only 1/3 of the promised strength. Everything else is right, so what happened to the vanilla? For cosmologists, lithium is that missing vanilla, a clue that something in our understanding of those first few minutes, or the subsequent history of this element, is not quite complete. Scientists have pursued 3 main paths to solve this puzzle, each taking them deeper into different branches of physics. The first possibility is that our knowledge of the nuclear physics itself is slightly off. The creation of lithium in the early universe depends on a specific chain of nuclear reactions, and the probabilities of these reactions occurring, known as nuclear cross-sections, are measured in sophisticated particle accelerator experiments. It is possible that there is a subtle, undiscovered nuclear reaction that destroyed some of the primordial lithium before it could stabilize, or that the measured rates for the known reactions have small, hidden uncertainties. Researchers are constantly refining these experiments, using ever more powerful accelerators to shrink the error bars and see if the numbers eventually converge with the astronomical observations. The second, and perhaps more popular, line of investigation points the finger at stars. The oldest stars in our galaxy, which we observe to measure the primordial lithium abundance, are not pristine time capsules. Over their billions of years of life, they have been churning and mixing their internal material. It is possible that these ancient stars have internal processes that slowly destroy lithium, dragging it from their surfaces down into their hotter interiors where it is fused into heavier elements. If our models of stellar physics are incomplete and don't fully account for this depletion mechanism, then we would be measuring a lithium level that is artificially low, not the true primordial value. The third and most thrilling possibility is that the lithium problem is a sign of new physics operating during the universe's infancy. Perhaps an unknown type of particle, such as a certain kind of dark matter, was present in the early cosmos and interacted with the nuclear soup, altering the reaction pathways and suppressing lithium production. Maybe the fundamental constants of nature, like the strength of the gravitational force, were slightly different in that first moment, creating a tiny but crucial deviation in the nuclear reaction rates. These are exotic solutions, but they are taken seriously because the lithium problem is such a clean and specific test of the Big Bang model. It connects the grand, cosmic scale of cosmology directly to the intimate, subatomic world of nuclear physics, forcing experts in these very different fields to collaborate. Nuclear physicists run their high-precision experiments in underground labs, while stellar astronomers point their telescopes at the most ancient stars in the halo of our galaxy, and cosmologists run complex computer simulations of the early universe. It is a truly interdisciplinary puzzle, where the answer may come from a conversation between scientists who, on the surface, seem to be studying entirely different things. This ongoing investigation is more than just an academic exercise in accounting. It is a powerful reminder of the dynamic and self-correcting nature of science. The lithium problem shows us that even a theory as successful and foundational as the Big Bang is not a closed book. Its unresolved details are not failures but opportunities, invitations to look deeper and discover something new. The quest to find the missing lithium drives technological innovation in both particle accelerators and telescopes, and it fosters a beautiful synergy between laboratory science and observational astronomy. Whether the ultimate solution involves a refined nuclear cross-section, a better model of stellar interiors, or a revolutionary new particle, the journey to find it sharpens our tools and deepens our understanding of the cosmos, from its very first violent moments to the ancient stars that illuminate our galactic night. Now, let's shift our focus to a fundamental pattern that holds galaxies together, a relationship so tight it feels like a cosmic rulebook, until we find the pages where that rulebook seems to have been torn out. This is the Tully-Fisher Relation, a beautifully simple correlation discovered in the 1970s that links a spiral galaxy's total brightness to how fast it spins. The logic seems intuitive. A brighter galaxy has more stars and therefore more mass. More mass means a stronger gravitational pull, which should whip the stars and gas on the galaxy's outskirts around at higher speeds. This connection between luminosity and rotation speed has been a cornerstone of astronomy for decades, a reliable tool for measuring the distances to far-off galaxies. But like so many things in cosmology, this neat and tidy picture begins to fray at the edges, revealing an anomaly that strikes right at the heart of our understanding of gravity itself. The problem arises when we look at certain galaxies that seem to be playing by a different set of rules. In these systems, the rotation speed is either too fast or too slow for their given brightness, breaking the expected Tully-Fisher relation. This breakdown isn't just a minor statistical scatter. It's a systematic deviation that suggests the gravitational force at work within these galaxies cannot be accounted for by the visible matter we see glowing within them. It's as if you had two cars with identical engines, but one was inexplicably speeding around a track while the other crawled, forcing you to conclude that an unseen force must be at work on one of them. This is precisely where the dark matter hypothesis has traditionally stepped in to save the day. The Standard Model posits that every galaxy is embedded within a vast, invisible sphere of dark matter, a halo whose gravity dominates the outer regions. This dark matter halo provides the extra gravitational glue that explains why the outer stars in spiral galaxies orbit so quickly. According to this view, the Tully-Fisher relation works because there is an underlying connection between the amount of visible matter in a galaxy and the size of its dark matter halo. A brighter galaxy with more stars is likely to reside within a more massive dark matter halo, resulting in a faster rotation curve. The relation holds as long as this coupling between luminous and dark matter is consistent. But when the relation breaks down, it suggests that this coupling might be more complex than we thought, or that the dark matter halo itself has an unexpected shape or distribution in certain galaxies. It forces cosmologists to ask difficult questions. Are there different types of dark matter halos? Could interactions between galaxies strip away or distort these halos, altering a galaxy's rotation in ways that violate the simple Tully-Fisher relation? This anomaly pushes the dark matter model to its limits, demanding more nuanced and detailed simulations to explain why some galaxies fall off the predicted line. The persistent failures of the standard dark matter model to explain every galactic quirk have given rise to a radically different and fiercely debated alternative. This is modified Newtonian dynamics, or MUND, proposed by physicist Mordechai Milgrom in the 1980s. MUND makes a bold claim: there is no dark matter. Instead, our understanding of gravity itself is incomplete. Newton's laws, and by extension Einstein's general relativity, work perfectly well in regions of strong gravity, like here in our solar system. Buttman proposes that in the extremely weak gravitational fields that exist in the outer reaches of galaxies, the laws of dynamics change. Milgrom suggested a simple modification. When the gravitational acceleration drops below a certain very low threshold, gravity begins to fall off more slowly than the traditional inverse square law would predict. This tiny tweak to the math has a profound consequence. It naturally produces the high rotation speeds observed at the edges of spiral galaxies without requiring any invisible matter. Even more impressively, the original MUND theory predicted the Tully-Fisher relation before it was even firmly established by observation. For its proponents, this is MUND's greatest triumph. It emerges naturally from the modified laws of physics, whereas in the dark matter model, the relation is something that must be explained by complex and often fine-tuned models of galaxy formation. Yet, for all its elegance on the scale of individual galaxies, MUND faces its own monumental challenges when we zoom out to the cosmos at large. The theory was specifically designed to fix the rotation curve problem, and it does that job remarkably well for many isolated spiral galaxies. However, the universe presents us with gravitational puzzles that span vastly different scales, and this is where MUN struggles to keep up. The most damning evidence against it comes from the Bullet Cluster, a spectacular collision of two galaxy clusters. During this cosmic crash, the hot, X-ray emitting gas from the two clusters slammed into each other and slowed down, but the vast majority of the mass, as mapped by gravitational lensing, sailed right through the collision and ended up far away from the gas. In the dark matter model, this makes perfect sense. The collisionless dark matter particles passed through one another, while the normal gas interacted and got stuck in the middle. For MUN, which attributes all gravitational effects to modified laws acting on visible matter, this observation is devastatingly difficult to explain. How can the source of the gravity be completely separated from the visible matter itself? Proponents of modified gravity have worked on sophisticated extensions to MUN to address this, but no solution has gained widespread acceptance. Furthermore, the precise patterns of the cosmic microwave background and the large-scale structure of the universe are exquisitely well fit by models that include cold dark matter, while MUN-based models have to introduce new, ad hoc fields to even come close to matching the data. This ongoing conflict is far from a stalemate. It is a vibrant driving force in modern observational astronomy, pushing our instruments to new heights of precision. The battle is fought with data, specifically by mapping the rotation curves of galaxies with incredible detail. This is where powerful radio telescopes like the Atacama Large Millimeter/Submillimeter Array, or Oumuamua, come into play. While optical telescopes see the light from stars, Oumuamua sees the faint radio emission from cold clouds of gas, primarily carbon monoxide, that trace the outer, dark regions of galaxies where stars are scarce. By measuring the Doppler shift of this radio light, astronomers can chart how fast this gas is orbiting the galactic center, constructing a complete and precise rotation curve from the bright inner core all the way out to the faint, tenuous outskirts. The goal is to gather this data for a huge diversity of galaxies, big and small, young and old, isolated and interacting, to see which theories' predictions hold up. Does the rotation curve always match the shape dictated by the visible mass plus a standard dark matter halo? Or does it consistently follow the distinctive pattern predicted by MUN-modified gravity formula? Each new galaxy mapped is another data point in this grand cosmological trial, and the results so far are a mixed bag, with some galaxies strongly favoring one model and others leaning toward the alternative, ensuring that the debate remains fiercely alive. This great controversy over the Tully-Fisher relation and the nature of gravity is more than just an academic disagreement. It is a powerful demonstration of how science progresses through tension and challenge. The anomaly forces both sides to refine their arguments and sharpen their predictions. Dark matter advocates are driven to create more realistic and complex computer simulations of galaxy formation, trying to understand how baryonic processes like supernova explosions and active galactic nuclei can feed back and influence the dark matter distribution, potentially explaining the outliers. Meanwhile, MUN proponents are inspired to develop more robust relativistic versions of their theory, such as tensor vector scalar gravity, in an attempt to reconcile their ideas with the broader successes of cosmology and the evidence from galaxy clusters. This dynamic back and forth has been incredibly productive. It has pushed for more precise measurements of galactic properties. It has highlighted the complex interplay between visible and dark matter, and it has kept scientists intellectually honest, preventing any single paradigm from becoming too comfortable or complacent. The Tully-Fisher anomaly, in all its complexity, shows us that galactic-scale phenomena are not just minor details. They are fundamental testing grounds that can challenge our deepest cosmological paradigms, inspiring the creation of entirely new theoretical frameworks and reminding us that our quest to understand the force that shapes the cosmos is far from over. But if dark matter makes up the invisible gravitational skeleton of the cosmos, and dark energy fuels its accelerating expansion, what about the stuff we're actually made of, the ordinary matter of stars, planets, and people? This brings us to a cosmic accounting error of a different kind, a puzzle known as the missing Baryon problem. Baryons are the familiar particles that constitute everything you can see and touch: protons and neutrons, the building blocks of atoms. Based on incredibly precise measurements of the cosmic microwave background, scientists can calculate the total amount of this ordinary matter that should have been created in the Big Bang. The universe's recipe is very specific, yet when astronomers add up all the baryons they can directly observe, all the stars twinkling in all the galaxies, all the glowing gas within and between them, and all the dusty nebulae, they come up dramatically short. We can only account for about half of the ordinary matter that our foundational models insist must be there. It's as if you took a detailed inventory of a vast warehouse, and the ledger showed 1,000 boxes shipped, but you could only find 500 on the shelves. The question is simple and profound. Where is the rest of the normal stuff? This isn't a search for some exotic, unknown substance. It's a hunt for the universe's lost atoms, a significant portion of the very material that should be right in front of us, yet has somehow managed to hide in plain sight. The leading suspect in this cosmic whodunit is not a single, massive object, but an incredibly diffuse and elusive component of the cosmic web known as the warm-hot intergalactic medium, or WIM. Picture the large-scale structure of the universe not as a collection of isolated islands, but as a vast, interconnected sponge. The galaxies and galaxy clusters are the dense knots and filaments of this sponge, but the vast spaces between them are not completely empty. Theorists predicted that a significant portion of the missing baryons should be in these voids, but not in a form that is easy to see. This material is thought to be a thin, incredibly hot gas, heated to temperatures between 100,000 and 10 million degrees Kelvin by the immense gravitational forces as matter collapsed into the cosmic web over billions of years. At these tremendous temperatures, the gas is so ionized, stripped of its electrons, that it doesn't emit the kind of visible light our telescopes are designed to catch. It's essentially invisible, like a ghostly, superheated fog filling the spaces between the glittering cities of galaxies. Finding this WIM is like trying to see the air in a room. You know it's there, but without the right tools, it remains completely transparent. So, how do you track down something that refuses to glow? Astronomers have had to become incredibly clever, developing indirect detection methods that rely on the subtle ways this hidden matter interacts with light from distant, brilliant sources. One of the most effective techniques is X-ray absorption spectroscopy. Imagine a distant quasar, a phenomenally bright beacon powered by a supermassive black hole, shining from the far reaches of the universe. As its powerful light travels across billions of light years to reach us, it passes through these invisible filaments of the WIM, the highly ionized atoms in this hot gas. Things like oxygen, neon, and nitrogen are very particular about the light they absorb. They will only grab onto very specific wavelengths of X-ray light. When scientists analyze the quasar's spectrum, they look for tiny, telltale dips in the intensity at these specific wavelengths. Each dip is like a fingerprint, revealing the presence and properties of a specific element in an otherwise invisible cloud of gas that the light passed through on its journey. It's a painstaking process, like identifying the ingredients in a distant soup by analyzing the shadow it casts on a single, specific color of light. A second and remarkably complementary technique has emerged from the study of the fleeting cosmic flashes we discussed earlier, fast radio bursts. As these intense radio waves race through the cosmos, they don't just tell us about their own mysterious origins, they also act as perfect probes for the material they travel through. The diffuse electrons in the WIM cause the different frequencies within the radio burst to spread out, with the lower frequencies arriving slightly later than the higher ones. By measuring this dispersion very carefully, astronomers can effectively count the total number of free electrons the signal encountered along its path. Since this warm, hot intergalactic gas is fully ionized, teeming with free electrons, each FRB provides a direct measurement of the density of ordinary matter in the vast intergalactic voids it traversed. When you have enough of these bursts from different directions, you can start to build a three-dimensional map of where the missing baryons are hiding, tracing the faint filamentary structure of the cosmic web itself. The combination of X-ray absorption and FRB dispersion is a powerful 1-2 punch in the hunt, allowing scientists to cross-check their results and build a convincing case that the WIM is indeed the final resting place for the universe's lost atoms. This grand search is far more than just an exercise in cosmic bookkeeping. It is a fundamental driver of technological and theoretical progress. The desperate need to detect the faint signature of the WIM is pushing the capabilities of ultraviolet and X-ray astronomy to their absolute limits. It is a primary scientific motivation for next-generation space telescopes, instruments that will be specifically designed with the sensitivity and spectral resolution to detect fainter absorption lines from more distant quasars, mapping the WIM across larger volumes of the universe and deeper back in time. At the same time, the problem fuels advancements in supercomputing. Cosmologists run immense simulations of the universe's evolution, virtual cosmos that model how gravity pulls ordinary matter along the dark matter scaffolding to form the cosmic web. These simulations make specific predictions about the temperature, density, and distribution of the WIM. By comparing these predictions with the actual observational data from FRBs and X-ray telescopes, scientists can test and refine our understanding of how the large-scale structure of the universe formed and evolved. This beautiful feedback loop between prediction and observation is the engine of modern cosmology. Ultimately, the quest to find the missing baryons underscores a pivotal shift in how we explore the cosmos. We are moving beyond simply looking at the things that shine and are learning to see the universe by the shadows it casts and the subtle imprints it leaves on passing messengers. It highlights the critical importance of indirect detection methods and the power of a multi-messenger approach, where we combine information from light, from radio waves, and from theoretical models to solve a puzzle that no single method could crack alone. Solving the missing baryon problem is the essential final step in validating the standard model of cosmology. Finding this hidden matter would be a triumphant confirmation that our understanding of the universe's composition and history is fundamentally correct. It would complete the cosmic inventory of ordinary matter, assuring us that the atoms we are made of are not lost, but simply waiting in the dark, hot spaces between the stars, an integral part of the grand, invisible architecture that binds the cosmos together. Now, let's journey from the hidden matter of the cosmos to the most energetic particles ever observed, projectiles of pure power screaming across the universe that challenge a fundamental limit we thought was absolute. These are ultra-high-energy cosmic rays, atomic nuclei traveling at a fraction of the speed of light, each carrying the punch of a professionally thrown baseball, all compressed into a single subatomic particle. The energies involved are almost incomprehensible, millions of times greater than anything we can produce in our most powerful particle colliders on Earth. For decades, physicists have had a compelling theory about how far this cosmic energy race can possibly go, a theoretical ceiling known as the Greisen-Zatzeping Kuzmin cutoff, or simply the GZK cutoff. The logic behind it is beautifully destructive. Imagine one of these incredibly energetic protons, a cosmic cannonball, racing across the vast expanse of the universe. The space between galaxies is not completely empty. It is filled with the faint relic photons of the cosmic microwave background, the afterglow of the Big Bang. For a proton with energy beyond the GZK limit, this cosmic fog becomes a minefield. When such an ultra-high-energy proton collides with one of these background photons, the interaction is so violent that it triggers a nuclear reaction, producing a shower of new particles, most notably a pion. This process robs the proton of a significant chunk of its energy. Over millions of light years, this should happen again and again, effectively eroding the energy of any cosmic ray that tries to travel a great distance. The GZK cutoff, therefore, acts like a cosmic speed limit, a fundamental barrier that should prevent us from seeing these ultra-high-energy particles from very far away. They should simply run out of steam before they ever reach our detectors. Yet the universe, in its characteristic fashion, seems to delight in breaking its own rules. When massive observatories like the Pierre Auger Observatory in Argentina or the telescope array in Utah began recording these cosmic rays, they found something that sent a ripple of excitement through the astrophysics community. They detected a handful of particles with energies that clearly surpassed the predicted GZK limit. It's as if we were monitoring a highway with a strict speed limit, and a few cars came blazing through at twice the maximum allowed speed. This is the GZK anomaly in a nutshell, a small but statistically significant group of particles that appear to have defied the cosmic drag race, arriving at Earth with energies they simply should not possess if they had traveled across billions of light years as we assumed. This isn't just a minor discrepancy, it's a direct challenge to our understanding of how particles interact and travel through the universe on the largest scales, forcing us to reconsider where these particles come from and what laws of physics they are obeying. This puzzling observation forces scientists to consider two radically different types of solutions, each with profound implications. The first, and more conservative, explanation is that these ultra-high-energy cosmic rays are not coming from the distant depths of the universe at all, but are relatively local visitors from our own cosmic backyard. If their journey was short, they wouldn't have had enough time to be slowed down by the countless collisions with the cosmic microwave background. This immediately launches a hunt for nearby cosmic accelerators capable of such mind-boggling feats of power. The prime suspects are active galactic nuclei, the incredibly energetic cores of galaxies where matter spiraling into a supermassive black hole is heated to immense temperatures and shot out in colossal jets. These jets could, in theory, act as natural particle accelerators on a galactic scale, capable of boosting particles to these extreme energies. Other potential local sources include shock waves from nearby galaxy clusters or even rare, hyper-energetic stellar explosions. The problem is that when astronomers trace the arrival directions of these anomalous cosmic rays back to their potential sources, they often don't find a clear, obvious candidate like a brilliant active galaxy sitting in the right spot. This lack of a clear, local source makes the anomaly even more intriguing and pushes us toward the second, far more exotic possibility. The alternative is that we are seeing the first hints of new physics beyond our current standard model. Perhaps the GZK cutoff itself is not as absolute as we believe because the laws of physics change at these extreme energies. One of the most compelling ideas is a violation of Lorentz invariance, a cornerstone of both Einstein's special relativity and the Standard Model. Lorentz invariance is the principle that the laws of physics are the same for all observers, regardless of their constant velocity. It's what gives us the cosmic speed limit of light in a vacuum. If this symmetry is slightly broken at energies approaching the Planck scale, the very fabric of spacetime might behave differently. In such a scenario, the interaction between the cosmic ray proton and the background photon that causes the energy loss might be altered or suppressed, allowing these particles to travel much farther than expected without slowing down. This would mean that the particles we see could indeed be coming from distant corners of the universe, and their survival is a message that our understanding of spacetime itself is incomplete, offering a potential window into the long-sought theory of quantum gravity. The GZK anomaly, therefore, transforms from a simple astrophysical puzzle into a potential laboratory for testing the most fundamental symmetries of nature. To untangle this mystery, scientists have built some of the most ambitious and vast experiments on the planet. The Pierre Auger Observatory, for instance, is not a single telescope but a sprawling network covering 3,000 square kilometers of Argentine prairie, an area larger than some small countries. It employs over 1,600 water tanks that sit waiting for the cascading showers of secondary particles created when an ultra-high-energy cosmic ray slams into the top of our atmosphere. By measuring the faint glow of Cherenkov radiation in these tanks and combining that data with fluorescence telescopes that watch the development of the air shower itself, the observatory can reconstruct the original particle's energy, direction, and even its mass with incredible precision. The telescope array in Utah uses a similar hybrid approach. The goal is to collect enough of these ultra-high energy events to see if they cluster in a specific direction, pointing back to a single source, or if they are isotropic, coming from all directions, which would favor the new physics explanation. This is painstaking work, as these highest energy events are incredibly rare, with perhaps just one particle per square kilometer per century arriving at the very top of the energy scale. Catching them requires immense patience and a detector of truly continental proportions. This quest does not exist in isolation. It beautifully illustrates the convergence of particle physics and astrophysics into a single, unified field. The GZK anomaly is a bridge connecting the behavior of subatomic particles to the large-scale structure and history of the cosmos. It probes energy regimes so extreme that the effects of quantum gravity, where the smooth geometry of general relativity meets the fuzzy uncertainty of the quantum world, might finally become apparent. Furthermore, the search for answers has spawned a new era of multi-messenger astronomy. Theorists predict that the same cataclysmic events that accelerate these cosmic rays should also produce two other cosmic messengers, high-energy neutrinos and gamma rays. If a cosmic ray interaction produces pions, as the GZK process predicts, those pions will decay into both neutrinos and gamma rays. Observatories like the Ice Cube Neutrino Observatory at the South Pole and gamma-ray telescopes like the Fermi Space Telescope are therefore essential partners in this investigation. By looking for a correlation between the arrival of an ultra-high-energy cosmic ray and a burst of neutrinos or gamma rays from the same patch of sky, scientists could finally pinpoint the engine responsible and understand the acceleration mechanism at work. The GZK mystery, in its defiance of a simple limit, pushes the entire field of high-energy astrophysics forward, driving the development of more sensitive detectors, more sophisticated theoretical models, and a more holistic view of the universe's most violent and energetic processes, reminding us that the greatest barriers often exist to be broken. Gravity, we are taught, is the force that keeps our feet on the ground, but in the grand cosmic theater, it is also the master sculptor of light itself. This phenomenon, known as gravitational lensing, is one of the most stunning confirmations of Einstein's theory of general relativity. It tells us that mass doesn't just pull on objects, it warps the very fabric of space-time, and light, traveling in a straight line through that warped fabric, follows a curved path. The result is that massive objects like galaxy clusters can act as natural cosmic magnifying glasses. They can bend, distort, and even multiply the light from more distant galaxies lying behind them, creating dazzling arcs, rings, and multiple images of a single object. It's a beautiful and powerful tool, allowing us to see galaxies so far away they would otherwise be invisible. But sometimes this cosmic lens doesn't behave exactly as our models predict. The light doesn't bend in quite the right way, or the brightness of the multiple images is off. These subtle discrepancies, these lensing anomalies, are like tiny cracks in a magnificent stained glass window, and through them we are catching glimpses of the invisible universe's hidden architecture. One of the most telling puzzles involves the flux ratios of multiply-imaged quasars. Imagine a brilliant, distant quasar, a beacon of light powered by a supermassive black hole. Its light travels toward us, but on the way, it passes by a massive foreground galaxy. The galaxy's gravity splits the single beam of light, creating 4 distinct images of the same quasar arranged in a cross-like pattern, a configuration known as an Einstein cross. According to our best models, which account for the gravity of the visible stars and gas in the foreground galaxy, we can predict how bright each of these 4 images should be. Yet, time and again, astronomers find that the observed brightness or flux of these images doesn't match the predictions. One image might be significantly dimmer than the model says it should be, while another is brighter. It's as if you were looking at yourself in a funhouse mirror, but instead of one distorted reflection, you see 4, and each one is warped in a different, unexpected way. This flux ratio anomaly is a stubborn signal that our map of the mass in that foreground galaxy is incomplete. There is gravity at work that we are not accounting for with the luminous matter we can see. So, what is causing this extra, unseen gravitational pull? The prime suspect is the dark matter halo that we believe surrounds every galaxy. The standard model, known as cold dark matter, posits that this halo is a vast, relatively smooth sphere of invisible particles. But the flux ratio anomalies suggest a far more textured and clumpy reality. It appears that these dark matter halos are not perfectly smooth. Instead, they are likely filled with a vast population of smaller subhalos, dense clumps of dark matter that could host their own faint dwarf galaxies or could be completely dark with no stars at all. As the light from the distant quasar travels through this lumpy, grainy dark matter halo on its way to our telescopes, these invisible clumps act like tiny additional lenses. They subtly alter the path of the light, minutely magnifying or demagnifying each of the quasar's images, throwing off the predicted flux ratios. It's the gravitational equivalent of light passing through a pane of glass that is not perfectly smooth, but is subtly rippled, distorting the image in a way that betrays the glass's hidden texture. These anomalies are the fingerprints of that invisible texture, the first direct evidence that dark matter is lumpy on small scales. This discovery has sent theorists back to their drawing boards, challenging the very nature of the dark matter particle itself. The simplest cold dark matter models, which have been incredibly successful at explaining the universe on the largest scales, predict a veritable jungle of these small-scale subhalos. But when we look for the faint dwarf galaxies that should be lighting up these clumps, we find fewer than expected. The lensing anomalies add another layer to this puzzle, suggesting the subhalos are there, but many are too dark to see. This has opened the door for compelling alternative theories. Perhaps dark matter isn't cold, but warm. warm dark matter would consist of lighter, faster-moving particles. This would naturally suppress the formation of very small clumps, resulting in a smoother distribution of matter on small scales that might better align with some observations. Another intriguing possibility is that dark matter is self-interacting. In this model, dark matter particles can actually collide and scatter off one another, much like molecules in a gas. These interactions would erode and smooth out the densest inner regions of dark matter clumps, effectively sanding down the sharpest gravitational features that cause the most dramatic lensing anomalies. The precise way that light is bent and brightened in these systems is giving us a direct, if subtle, probe into the fundamental properties of the universe's most mysterious constituent. To move from suspicion to confirmation, we need to see this hidden substructure directly, and that requires pushing our telescopes to their absolute limits. This is where the legendary Hubble Space Telescope and its revolutionary successor, the James Webb Space Telescope, enter the fray. Hubble, with its crystal-clear vision from Earth orbit, has been meticulously studying known gravitational lenses for years, creating exquisitely detailed maps of these cosmic mirages. But JWST, with its profound infrared sensitivity and razor-sharp resolution, is a game-changer. It is now peering deep into the heart of these lensing galaxies, hunting for the faint, stellar glow of the very dwarf satellites that the dark matter subhalos are predicted to host. Finding these faint galaxies would provide a direct, visible correlation to the gravitational anomalies we detect. Even more powerfully, JWST can use a technique called gravitational microlensing within these larger systems. If a dark, starless clump of dark matter drifts in front of one of the magnified quasar images, it could cause a brief, telltale twinkle in its brightness, a fleeting signal that we have found a truly dark substructure. This is the new frontier of dark matter hunting, using gravity's own lens not just to see the invisible, but to map its granular details. The pursuit of these ghostly signatures is driving a parallel revolution in how we analyze the sky, through the sophisticated techniques of strong and weak gravitational lensing. Strong lensing, which produces those beautiful, unmistakable arcs and multiple images, is relatively rare, requiring a near-perfect alignment between a distant source and a massive foreground object. But weak lensing is everywhere. It is a far more subtle effect, where the light from countless background galaxies is very slightly stretched and sheared by the cumulative gravity of all the matter, both light and dark, that lies between them and us. No single galaxy shows a dramatic distortion, but by studying the coherent, statistical alignment of millions of galaxies across a vast patch of sky, astronomers can create a mass map of the cosmos. This weak lensing technique is like feeling the texture of a surface with your eyes closed by dragging your hand across it. You can't see the individual bumps and grooves, but you can clearly feel its overall topography. By combining the detailed, small-scale puzzles of strong lensing with the vast, statistical power of weak lensing surveys, we are building a three-dimensional census of dark matter from the scale of individual galaxies all the way up to the cosmic web itself. This entire field of research beautifully demonstrates that we do not need to capture a dark matter particle in a lab to understand its nature. We can simply watch how it interacts with the one force we know it must feel: gravity. The unexpected ways in which it bends light are not failures of our theories, but rather precise diagnostics. Each anomalous flux ratio, each subtly sheared galaxy, is a data point that tells us about the mass, the temperature, and the possible interactions of the dark world. Lensing anomalies provide a unique window into dark matter properties on scales that are simply inaccessible to other methods, complementing the searches in underground laboratories and particle colliders. They show us that the invisible universe is not a featureless void, but a dynamic landscape of dark mountains and valleys, whose contours are slowly being revealed by the delicate dance of light traveling through the curved tapestry of spacetime. Of all the denizens of the subatomic world, the neutrino is perhaps the most ghostly and elusive. For decades, these particles were thought to be true phantoms, zipping through the universe at the speed of light and slipping through entire planets as if they weren't even there. The Standard Model of Particle Physics, our most complete catalogue of the universe's fundamental building blocks, enshrined this belief, classifying neutrinos as completely massless. But then, a series of exquisitely sensitive experiments delivered a result so shocking it forced a rewrite of the textbooks. We discovered that neutrinos have a bizarre and unique party trick. They can change their identity as they travel. An electron neutrino produced in the heart of the Sun can, by the time it reaches Earth, transform into a muon neutrino or a tau neutrino. This phenomenon, called neutrino oscillation, is only possible if these phantoms have mass, however vanishingly small. This was the first concrete crack in the seemingly impervious Standard Model, an elegant and powerful theory that now had to admit it was incomplete. The simple, massless ghost was gone, replaced by a profound puzzle. If neutrinos have mass, how much do they weigh, and what does this mean for the very foundations of physics? Pinning down the actual weight of these cosmic wraiths has proven to be one of the most frustrating challenges in modern science. Neutrino oscillation experiments are brilliant at revealing that mass exists, but they are like a scale that can tell you the difference in weight between three objects without being able to tell you the actual weight of any single one. They measure the differences in the squares of the masses between the three known types or flavors of neutrinos. This leaves two colossal questions wide open. The first is the absolute mass scale. We know the masses are incredibly tiny. A single neutrino is at least 10 million times lighter than an electron, itself a featherweight particle. But is the total mass of all three neutrinos combined equivalent to a few tenths of an electronvolt, or is it closer to 1 electronvolt? The second great unknown is the ordering of this tiny mass. Imagine 3 boxes of unknown weight. We know that box 2 is heavier than box 1, and we know the mass difference between box 3 and the others, but we don't know if box 3 is the heaviest of all or the lightest. This is the neutrino mass ordering problem. Is the third neutrino the heavyweight in what's called the normal hierarchy, or is it the lightest in an inverted hierarchy? The answer to this seemingly esoteric question has earth-shattering implications for why our universe is built the way it is. This is not just a problem for particle physicists hunched over detectors in deep underground labs. It is a question that echoes across the entire cosmos. While an individual neutrino is almost impossibly light, they are also almost impossibly numerous. In the first second after the Big Bang, the universe created a staggering flood of neutrinos, a cosmic background that still permeates all of space, with billions passing through your thumbnail every second from the Sun alone. This vast sea of lightweight particles, all moving at nearly the speed of light, has a profound gravitational effect on the evolution of the universe's large-scale structure. In the early cosmos, neutrinos acted like a kind of cosmic dark energy, their relentless speed preventing them from clumping together in the gravitational wells that were trying to form the first galaxies and clusters. This suppressed the growth of the very smallest structures. The precise pattern of galaxy clusters we see etched across the sky today, and the subtle fluctuations in the cosmic microwave background, bear the imprint of this neutrino influence. By studying these ancient fossils with observatories like the Planck satellite, cosmologists can place an upper limit on the sum of all neutrino masses. The current data tells us that the combined mass of the three neutrinos must be less than about 0.2 electron volts. This is a powerful constraint, a fence that any successful theory of neutrino mass must fit inside, beautifully tying the behavior of the smallest particles to the grandest structures in existence. To break the deadlock and measure the neutrino's mass directly, rather than through its cosmic influence, scientists have engineered some of the most precise machines ever conceived. The flagship of this direct search is the Katrin experiment, the Karlsruhe tritium neutrino experiment in Germany. Katrin approach is one of breathtaking precision. It uses a giant, multi-story spectrometer to study the radioactive decay of tritium, a heavy isotope of hydrogen. In this decay, a tritium nucleus transforms, emitting an electron and an electron antineutrino. The total energy released in the decay is fixed, but it is shared between the electron and the neutrino. By measuring the very highest energy electrons produced with exquisite accuracy, Katrin can deduce the energy that was not carried away by the electron. Any missing energy beyond what is accounted for must be the mass of the neutrino. It is a monumental task, akin to weighing a single snowflake by precisely measuring the weight of a mountain before and after it lands. Katrin has already placed the world's best direct limit, confirming that the electron neutrino's mass is less than 0.8 electron volts. It is now entering a new phase of sensitivity, poised to either detect the definitive fingerprint of neutrino mass or push the limits even further, inching closer to the value suggested by the cosmos itself. The very existence of neutrino mass is more than just a new fact. It is a blazing signpost pointing toward physics beyond the standard model. The original model provided no mechanism for neutrinos to have mass, so its discovery forces us to invent new theories. One of the most compelling ideas is the seesaw mechanism. This elegant proposal suggests that the incredibly tiny masses of the neutrinos we see are a direct consequence of the existence of incredibly heavy, undiscovered particles. In this model, the lightness of the ordinary neutrino is balanced, or seesawed, against the tremendous mass of a hypothetical sterile neutrino, a particle that doesn't even feel the weak nuclear force. If these heavy sterile neutrinos exist, they would have been produced in the searing heat of the Big Bang, and their subsequent decay could be the very reason our universe is made of matter and not antimatter. This process, known as leptogenesis, posits that the asymmetric decay of these heavy neutrinos in the early universe preferentially created more matter than antimatter. Every atom, every star, every planet, and every one of us may ultimately be here because of the peculiar, seesawing physics of the neutrino. This creates a breathtaking bridge between a subatomic measurement in a lab and the ultimate existential question of why anything exists at all. The relentless pursuit of the neutrino's weight is therefore far more than an academic exercise. It is a powerful engine for technological revolution. The need to detect these ghostly particles has driven the creation of entirely new classes of detectors. We have built enormous tanks of ultra-pure water or liquid scintillator, buried deep underground to shield them from cosmic rays, and lined with thousands of sensitive light detectors to catch the faint flash of light when a neutrino rarely interacts. Experiments like Super Kamiok and in Japan and the Sudbury Neutrino Observatory in Canada were pioneers in this field. The next generation, such as the Deep Underground Neutrino Experiment, or DUNE, in the United States, will use vast volumes of liquid argon kept at cryogenic temperatures to achieve even greater sensitivity. These technological marvels are not just neutrino hunters, they are also watchmen for the final, catastrophic moments of dying stars, as a supernova's neutrino burst would wash through these detectors, giving us a real-time view into the heart of a collapsing star. The quest to solve the neutrino mass puzzle is pushing the boundaries of ultra-sensitive measurement, quantum sensors, and massive data analysis, creating tools and techniques that ripple out to benefit other fields of science and engineering. Ultimately, the story of the neutrino mass puzzle is a profound lesson in cosmic connectedness. It demonstrates with stunning clarity that the laws governing the smallest pieces of the universe are inextricably linked to its largest-scale evolution. A measurement made in a painstakingly controlled laboratory in Germany or South Dakota can decide between competing theories for how the entire cosmos evolved from a hot, dense state to the structured universe of galaxies we see today. The tiny, elusive neutrino, once thought to be a mere spectator in the cosmic drama, is now revealed as a key player, its minuscule mass holding sway over the fate of galaxies and the very existence of matter. Solving this mystery will not just fill in a missing parameter in a table, it will guide us toward the next, deeper theory of reality, one that can finally explain why these ghostly particles, against all odds, carry just enough weight to shape everything. Picture this, the universe in its first fleeting fraction of a second, not just expanding but erupting in a violent, exponential growth spurt that stretched the very fabric of space-time itself. This is the theory of cosmic inflation, and if it's correct, this cataclysmic event should have sent powerful ripples through the cosmos' primordial gravitational waves. These aren't waves in water or sound in air. They are literal vibrations in the geometry of reality, stretches and squeezes in the grid of space and time. And just as the Big Bang left behind a thermal photograph, the cosmic microwave background inflation should have left its own, far more subtle signature imprinted on that ancient light. This signature is what cosmologists are desperately hunting for, a specific pattern known as B-mode polarization. Finding it would be like discovering the fossilized footprints of the universe's very first moment, a direct glimpse into an energy regime so extreme that all the fundamental forces of nature were likely unified into one. The hunt for this signal is one of the most ambitious and technically daunting quests in all of modern science, a pursuit that perfectly illustrates the immense challenge of separating a whisper of cosmic truth from a roaring cacophony of celestial interference. To understand what makes this search so difficult, you first have to understand what B-mode polarization actually is. Think of the cosmic microwave background light as a vast, gentle sea of radio waves washing over us from every direction. This light can be polarized, meaning its electric fields don't just vibrate randomly. They have a preferred orientation, like the light reflecting off a lake. This polarization comes in two fundamental types. The first, called E-mode polarization, is a relatively simple pattern, like the radiating lines of a spiderweb or the electric field around a charged particle. It's primarily generated by the density fluctuations in the early universe, the same lumps that would eventually grow into galaxies. It's a curl-free pattern, and we've mapped it beautifully. The second type, B-mode polarization, is far more elusive. This pattern has a distinctive, swirly character, a curl like the pattern of water swirling down a drain. This specific handed swirl is the unique fingerprint that can only be created by a gravitational wave. As a primordial gravitational wave passes through the primordial plasma, it doesn't just shake the particles, it shears and twists the very light they emit, stamping this telltale swirling polarization onto the cosmic microwave background for all time. Finding these swirls on the sky is the ultimate goal, a direct signal from the inflationary epoch itself. The story of this hunt took a dramatic and headline-grabbing turn back in 2014, when the team behind the BICEP 2 telescope, located at the South Pole, announced a monumental discovery. They believed they had found it, the first definitive detection of primordial B-mode polarization. The scientific community and the world held its breath. This was the smoking gun for inflation, a window into the universe a mere 10 to the negative 36 seconds after its birth. The data seemed compelling, a clear swirly pattern that matched theoretical predictions. However, that initial euphoria was short-lived. A more detailed joint analysis with the European Space Agency's Planck satellite revealed a heartbreaking complication. The signal BICEP 2 had detected wasn't purely from the dawn of time. It was heavily contaminated by a much more local and far more mundane source, interstellar dust right here in our own Milky Way galaxy. This dust, made up of tiny, elongated grains of carbon and silicate, is not just a blocker of light, it can also polarize it. As these dust grains align with the galaxy's magnetic field, they act like countless tiny polarizing filters, and they too can produce a swirly B-mode pattern that is virtually indistinguishable from the primordial one. The universe's greatest secret was being hidden in plain sight by the dirt in our own cosmic backyard. This sobering experience taught cosmologists a brutal but invaluable lesson about the perils of systematic error. It showcased, in the most dramatic way possible, how an effect that perfectly mimics new physics can arise from an incomplete understanding of our own observational environment. The B-mode signal from inflation is incredibly faint, a subtle whisper on the sky. The signal from galactic dust, however, can be orders of magnitude stronger, especially in certain regions. It's like trying to hear a single, soft violin note in a symphony hall while standing right next to a roaring jet engine. You can't just listen for the violin. You have to find a way to precisely measure the roar of the jet engine and subtract it from the total sound with absolute perfection. Any error in that subtraction, any misestimation of the dust properties, and you will be left with a false signal, a phantom of new physics born from our own imperfect data cleaning. This anomaly, the confounding mimicry by foreground dust, has become the central problem of the field, forcing a complete overhaul of how we approach this cosmic detective work. In response, the entire endeavor has pivoted towards a new level of rigor and technological sophistication. The key to separating the cosmic signal from the galactic noise is multi-frequency observation. Galactic dust doesn't just polarize light, it does so in a way that has a very specific color or frequency signature. It glows most brightly and polarizes most strongly at higher frequencies, in the realm of infrared and high-frequency radio waves. The primordial B-mode signal, in contrast, has a blackbody spectrum. It looks the same at all frequencies, just like the rest of the cosmic microwave background. This difference is our only lifeline. Modern experiments no longer look at the sky with just one color of radio eye. They are now equipped with a whole suite of detectors that observe the same patch of sky across many different frequencies simultaneously, from low-frequency radio waves to high-frequency microwaves. By meticulously comparing the maps at all these different frequencies, scientists can build a precise model of the dust, its distribution, its temperature, and its polarization properties, and then, with painstaking care, subtract its contaminating glow from the total signal. What remains, if we are incredibly lucky, might be the pristine, multi-frequency consistent whisper of inflation. This monumental challenge is the direct driving force behind the next generation of cosmic microwave background observatories, most notably the upcoming CMB-S4 project. CMB-S4 is not a single telescope, but a colossal coordinated effort, a veritable army of telescopes planned for deployment in the pristine, dry air of the Chilean Atacama Desert and at the South Pole. This project represents a quantum leap in capability. It will feature hundreds of thousands of ultra-sensitive detectors, giving it an unprecedented mapping speed and sensitivity. But just as importantly, it will observe the sky across an even wider range of frequencies than ever before, providing the most detailed and robust foreground model imaginable. The goal is to move from a tentative maybe to a definitive 5 sigma discovery. This is big science at its most ambitious, an international collaboration pooling resources and intellect to overcome one of the most fundamental noise problems in the history of cosmology. The quest for B-modes is pushing the limits of detector physics, cryogenics, and big data analysis, creating technological spin-offs that benefit other fields while relentlessly pursuing its primary, universe-defining goal. The profound importance of this search extends far beyond simply confirming that inflation happened. Detecting these primordial gravitational waves would do something even more extraordinary. It would reveal the energy scale at which inflation occurred. The strength of the B-mode signal is directly tied to the energy density of the universe during that explosive inflationary period. A strong detection would tell us that inflation was driven by physics at an energy scale 1 trillion times higher than what the Large Hadron Collider can probe. It would be our first and only direct experimental window into the realm of grand unified theories and quantum gravity, an energy domain where the strong, weak, and electromagnetic forces were likely merged into a single, sublime unity. Furthermore, it would provide the ultimate link between the quantum and the cosmic. The primordial gravitational waves themselves are thought to be the result of quantum fluctuations, tiny, spontaneous jitters in the fabric of spacetime, that were born on subatomic scales and then stretched to cosmic proportions by inflation. These quantum jitters, once amplified, became the gravitational waves that twisted the cosmic microwave background, and the density fluctuations that seeded every galaxy, star, and planet. Finding the B-modes would complete this breathtaking story, connecting the ghostly, probabilistic world of the quantum to the majestic, large-scale structure of the entire universe, showing us that everything we see around us ultimately grew from the tiniest possible seeds sown in the first moment of time. Now we arrive at a question that is so fundamental it seems to question the very architectural blueprint of reality. It's known as the hierarchy problem, and it asks something that sounds deceptively simple. Why is gravity so incredibly, almost absurdly, weak? To truly feel the weight of this puzzle, consider the forces that govern your daily life. The electromagnetic force is what holds the atoms in your body together. The strong nuclear force binds the protons and neutrons in the nucleus of those atoms. These are powerful, dominant influences, but gravity, the force that holds entire planets and galaxies together, feels weak. You can overcome the gravitational pull of the entire Earth just by picking up a book. This isn't just a feeling, it's a staggering mathematical fact. The strength of gravity is about 1,000 trillion times weaker than the electromagnetic force. To put that in perspective, it's the difference between the energy of a single mosquito's flight and the total explosive energy of a supernova. This isn't a minor discrepancy, it's a chasm of such immense proportions that it suggests something profound is missing from our understanding of how the universe is built. This problem is crystallized in the comparison of two fundamental energy scales in physics. On one hand, you have the electroweak scale. This is the energy at which the electromagnetic force and the weak nuclear force unite into a single electroweak force, and it's an energy we can probe with our most powerful particle colliders, like the Large Hadron Collider. It's the energy realm of the Higgs boson. On the other hand, there is the Planck scale. This is the energy at which gravity is theorized to become as strong as the other forces, a domain where the quantum nature of spacetime itself becomes apparent. The Planck scale is a staggering 16 orders of magnitude. That's a factor of 10 million trillion higher than the electroweak scale. The problem is that in our current standard model of particle physics, these two scales should naturally want to be much closer together. The Higgs field, which gives particles their mass, is incredibly sensitive to these ultra-high energy effects. In theory, quantum fluctuations from the Planck scale should flood down into our low-energy world and dramatically inflate the mass of the Higgs boson, and by extension, the electroweak scale, pushing it to within a hair's breadth of the Planck scale itself. For our universe to exist as it does, with a light Higgs and a weak electroweak force, an absurdly precise and unnatural cancellation of these quantum effects must occur. It's as if you had a pencil perfectly balanced on its tip, and it just stayed there forever, defying the slightest breeze or vibration. This degree of fine-tuning seems so incredibly unlikely that physicists are convinced a deeper explanation must exist. This is where the search for new physics begins in earnest, and the leading candidate for decades has been a beautiful, symmetrical idea known as supersymmetry. Supersymmetry, or SUSY for short, proposes that for every known particle in the Standard Model, every quark, every electron, every photon, there exists a superpartner. An electron has a selectron, a quark has a squark, a photon has a photino. These superpartners would have different spin properties, but if this symmetry were unbroken, they would have the same mass. The magic of supersymmetry is that these superpartners would produce their own quantum fluctuations that precisely cancel out the problematic ones from the Planck scale. The fine-tuning would be solved naturally and elegantly. The hierarchy problem would simply vanish. It's a breathtakingly beautiful solution. Furthermore, the lightest of these supersymmetric particles is a perfect candidate for the mysterious dark matter that pervades our galaxy, offering a potential 2-for-1 answer to two of physics' greatest puzzles. The only catch is that for this cancellation to work perfectly, these superpartners must be relatively light, with masses not too far above the electroweak scale, which means we should have found them by now at the Large Hadron Collider. The fact that we haven't yet is a source of great tension, forcing physicists to consider more complex, broken versions of supersymmetry or to look elsewhere for answers. Another mind-bending possibility is that gravity only seems weak because it is not confined to our familiar 3 dimensions of space. This is the core idea of theories with extraspatial dimensions. Imagine our universe is a 3-dimensional membrane, or brain, floating within a higher dimensional space. The strong nuclear force and the electromagnetic force are stuck on our brain, which is why they appear so potent to us. But gravity, which is the curvature of spacetime itself, can leak out into these extra dimensions. From our perspective trapped on the brain, the gravitational force would be diluted, spread thin across the higher dimensional bulk, explaining its apparent feebleness in our world. In some of these models, the true Planck scale where gravity becomes strong could actually be much lower, even down at the electroweak scale. This would mean that the hierarchy problem is an illusion, a consequence of our limited 3-dimensional perspective. The implications are staggering. If this is true, then the Large Hadron Collider could potentially produce microscopic black holes or see evidence of gravitons, the particles of gravity, disappearing into these extra dimensions, providing an experimental signature that would forever change our conception of reality. When such elegant, testable ideas like supersymmetry and extra dimensions remain elusive, some theorists are driven to consider explanations that are far more philosophical in nature. This is where the multiverse and the anthropic principle enter the discussion. The multiverse hypothesis suggests that our universe is just one of a vast, perhaps infinite, ensemble of universes, each with different physical constants and laws. In this cosmic landscape, the strength of gravity and the mass of the Higgs boson would be different in every universe. In the overwhelming majority of these universes, the numbers would be wrong for the formation of atoms, stars, planets, or life. We find ourselves in a universe with an improbably weak gravity and a light Higgs, not because of a beautiful underlying symmetry, but simply because it is one of the rare universes where the conditions are just right for us to exist and ask the question. This anthropic reasoning offers an explanation, but for many scientists, it feels like a surrender. It moves the problem from the realm of predictive, testable physics to one of pure metaphysics, and it drives a deep division in the physics community about what constitutes a valid scientific explanation. The power of the hierarchy problem is that it is not an isolated puzzle. It is deeply intertwined with the other cosmic anomalies we have explored. The nature of dark matter, for instance, could be the very clue that points us toward the solution. If dark matter is indeed a supersymmetric particle, like the Neutrino, then its detection in an underground lab or its production at a collider would not only solve the dark matter mystery, but would also provide the first concrete evidence for the new physics required to resolve the hierarchy problem. Similarly, the phenomenon of cosmic inflation is thought to have occurred at energies far above the electroweak scale, potentially brushing against the realm where quantum gravity operates. The detection of primordial gravitational waves in the cosmic microwave background would give us a direct probe of that energy scale, telling us if the forces truly did unify and providing crucial data to test these grand unified theories. Even the bafflingly small value of the cosmological constant, the vacuum energy driving the universe's acceleration, is a hierarchy problem in its own right, and its solution may be linked to the same new physics that explains gravity's weakness. These cosmic puzzles are not separate. They are different facets of the same profound mystery, forcing us to develop ideas that can unite the quantum world with the cosmos. This is why the hierarchy problem remains one of the most active and driving forces in all of fundamental physics. It is the engine behind the multi-billion-dollar collider experiments that smash protons together at unprecedented energies, desperately searching for any deviation from the standard model, any new particle or force that could provide a clue. It is the motivation for deeply sensitive dark matter detectors buried miles underground, waiting for a whisper from the hidden world, and it inspires astronomers to build ever more powerful telescopes to peer back to the universe's first moments, seeking clues in the patterns of the cosmic microwave background and the large-scale distribution of galaxies. The hierarchy problem is more than just a technical issue. It is a profound challenge to our understanding of naturalness. It asks why the laws of physics seem so delicately balanced, and whether that balance is the result of a beautiful, underlying symmetry we have yet to discover, a consequence of our place in a vast multiverse, or a sign that our current theories are merely a shadow of a much deeper, more unified reality waiting to be found. If you think the vast emptiness of space is truly empty, think again. According to our best understanding of the quantum world, the vacuum of space is a seething, bubbling, and wildly energetic place. It is a vibrant sea of virtual particles that constantly wink in and out of existence, borrowing energy from the void for the briefest of moments before annihilating each other and disappearing. This is not some fringe idea. It is a fundamental prediction of quantum field theory, and it has been confirmed by measurable effects like the Casimir effect, where two metal plates placed incredibly close together in a vacuum feel a subtle push from the energy of these virtual particles popping into being in the space around them. When physicists calculate the total energy density that this frantic quantum activity should contribute to every cubic centimeter of seemingly empty space, they arrive at a number. And this number is, without exaggeration, the single worst prediction in the entire history of science. The theoretical value for this vacuum energy is about 10 to the power of 120 times larger than the energy density we actually observe for dark energy, the force driving the universe's accelerating expansion. To try and comprehend the scale of this error, imagine predicting the weight of a single electron and getting an answer that suggests it weighs more than the entire observable universe. This isn't just being off by a little, it is a discrepancy of such monumental proportions that it has been given a name worthy of its catastrophic failure, the Vacuum Catastrophe. This chasm between prediction and reality is also known as the cosmological constant problem, and it represents a direct and furious clash between our two most successful theories of reality. On one hand, you have quantum mechanics, which describes the frantic, probabilistic world of the very small with stunning accuracy. Its prediction for the vacuum energy is a straightforward calculation from its core principles. On the other hand, you have general relativity, Einstein's theory of gravity, which describes the smooth, geometric curvature of spacetime on cosmic scales with equal brilliance. When we plug the observed value of dark energy into Einstein's equations as the cosmological constant, it works perfectly to explain the accelerating universe. But when we try to feed the quantum field theory prediction into those same equations, the result is nonsensical. A vacuum energy that large would have generated so much repulsive gravity that it would have torn the universe apart in its first instance, preventing any stars, galaxies, or life from ever forming. The fact that we exist to measure this discrepancy means that something is profoundly wrong. Either our understanding of the quantum vacuum is fundamentally flawed, our theory of gravity is incomplete on cosmic scales, or, most likely, both. The vacuum catastrophe is the undeniable proof that quantum mechanics and general relativity, the twin pillars of modern physics, cannot both be correct in their current forms when it comes to the energy of nothingness. Faced with this impossible impasse, physicists have been forced to consider some truly radical solutions. One compelling line of thought is that there exists a mysterious cancellation mechanism, a kind of cosmic symmetry we have not yet discovered that perfectly nullifies the enormous quantum vacuum energy, leaving behind only the tiny, residual value we observe as dark energy. Imagine a seesaw with a colossal weight on one end, representing the theoretical vacuum energy. For the seesaw to be balanced, as our universe seems to be, there must be an equally colossal, but hidden, negative energy on the other end to cancel it out, leaving just a tiny speck of positive energy behind. The challenge is that no one has found a natural way to create this perfect cancellation within our current theories. Another prominent idea is that dark energy is not a constant vacuum energy at all, but something dynamic. This is the concept of quintessence, a name inspired by the fifth element of ancient philosophy. Quintessence proposes that dark energy is a field that permeates all of space, much like the Higgs field, but one that can change in strength and density over time. In this model, the energy density of the vacuum could have been different in the past and may evolve in the future, potentially avoiding the need for a single, finely tuned constant. While quintessence offers a way out of the fine-tuning problem, it too requires its own set of assumptions and so far lacks direct experimental evidence. The sheer magnitude of the vacuum catastrophe has made it a central driving force behind the most ambitious and speculative theories in physics, theories that aim to finally unite gravity with the quantum world. String theory, for instance, posits that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. In the complex landscape of possible solutions in string theory, there might exist a configuration where the various fields and dimensions conspire to produce a net cosmological constant that is very small, even zero. The hope is that our universe simply happens to reside in one of these rare pockets where the vacuum energy is minuscule, an idea that connects back to the multiverse concept. Another leading approach, loop quantum gravity, attempts to quantize space and time itself, suggesting that spacetime has a discrete, granular structure at the smallest possible scale, the Planck length. In this framework, the frenetic energy of the quantum vacuum might be naturally tamed or renormalized by the fundamental graininess of space, preventing it from reaching those unimaginably high levels. These theories represent humanity's most profound attempts to climb out of the hole dug by the vacuum catastrophe, but they remain, for now, incredibly difficult to test experimentally. What makes this anomaly so persistent and so humbling is that it exists within one of our most successful cosmological models. The lambda-cold dark matter model, or lambda CDM, which includes the cosmological constant lambda, describes the evolution and composition of our universe with breathtaking accuracy, matching observations from the cosmic microwave background to the large-scale distribution of galaxies. Yet, at its very heart lies this vacuum catastrophe, a problem so severe that it suggests our entire understanding of nothing is wrong. It is a stark reminder that scientific models can be incredibly successful at describing the what of the universe, its behavior and its history, while remaining completely in the dark about the why of its fundamental parameters. The vacuum energy is not a peripheral detail. It is the dominant component of the universe's energy budget, and we have no compelling explanation for why it has the specific, tiny value that it does. This puzzle forces a profound sense of humility, showing us that for all our knowledge, we are still grappling with the most basic questions about the nature of empty space and the forces that shape cosmic destiny. Ultimately, the quest to resolve the vacuum catastrophe is about more than just fixing a calculation. It is a journey to the heart of physical reality. Solving it would require a revolution as profound as those sparked by quantum mechanics or relativity themselves. It would mean discovering a theory of quantum gravity that seamlessly blends the world of the very small with the realm of the very large. A theory that would finally explain how the frantic quantum buzz of the microscopic world gives rise to the serene, geometric curvature of spacetime on a cosmic scale. The resolution of this single anomaly could unlock a new chapter in physics, revealing a universe far more interconnected and wondrous than we currently imagine. It might show us that the vacuum is not empty, but filled with a hidden structure and dynamics that dictate the ultimate fate of everything. Until then, the vacuum catastrophe stands as the universe's greatest outstanding bill, a glaring reminder that the energy of nothing is the something we understand least of all. From the ghostly tug of dark matter to the inexplicable chill of the cosmic cold spot, we are constantly confronted with cosmic anomalies that seem to demand an explanation beyond our single, observable universe. What if the answer to these profound puzzles isn't found within our cosmos, but outside of it? This is the breathtaking leap of thought that leads us to the Multiverse Hypothesis, a radical idea proposing that our universe is not the only one, but merely one bubble in a vast, frothing cosmic ocean of universes, each with its own unique physical laws and constants. The motivation for such a mind-bending concept often begins with the unsettling perfection of our own reality. Consider the precise tuning of the universe's fundamental forces. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself long ago. If the strong nuclear force were marginally weaker, atomic nuclei would never have formed. The cosmological constant, the value of dark energy, is fine-tuned to an accuracy of 1 part in 10 to the power of 120. This degree of perfection seems astronomically improbable, like winning the lottery 1 billion times in a row. The multiverse offers a compelling way out of this improbability. If there are an infinite number of universes, each with randomly dialed physical constants, then it's no surprise that we find ourselves in one of the rare, habitable ones where the numbers just happen to come out right for stars, planets, and life to emerge. We are not the winners of a cosmic lottery. We are simply the inhabitants of a universe that could support our existence, a concept known as the anthropic principle. This speculative vision doesn't emerge from a vacuum. It is a natural, though controversial, consequence of our most ambitious physical theories. The leading engine for generating a multiverse is the theory of eternal inflation. This suggests that the rapid, exponential expansion of space known as inflation did not happen just once in our universe. Instead, it may be an endless, ongoing process. In this picture, the fabric of spacetime is like a constantly rising loaf of raisin bread, where each raisin is a separate, self-contained universe. Inflation ends locally in a patch, creating a bubble universe like our own, while the space between bubbles continues to inflate eternally, spawning an endless number of new cosmic domains. Another fertile ground for the multiverse is string theory, which attempts to unify all forces and particles. String theory predicts not one, but a colossal number of possible stable configurations for the extra dimensions it requires, perhaps 10 to the 500 different versions. This string landscape presents a vast array of potential universes, each corresponding to a different set of physical laws and constants. Our universe, then, would be just one tiny valley in this incomprehensibly vast landscape of possibilities. The multiverse, therefore, is not a single idea but a framework that emerges when we push our best theories to their logical extremes, suggesting that the ultimate reality is far grander and more diverse than the single spacetime continuum we call home. A hypothesis this profound inevitably draws fierce criticism, with the most common charge being that it is not proper science because it is fundamentally untestable. If other universes are forever beyond our observational reach, separated by inflating space or higher dimensions, how can we ever confirm their existence? Doesn't this idea fall into the realm of metaphysics rather than empirical science? Proponents of the multiverse counter this by actively searching for potential signatures, cosmic scars that could have been imprinted on our universe from a primordial encounter with another. One of the most promising ideas involves looking for the aftermath of a cosmic bubble collision. In the eternal inflation scenario, as new bubble universes nucleate and expand, they might occasionally collide with one another. Such a titanic impact would have sent powerful ripples through the infant cosmos, potentially leaving a distinct, asymmetric pattern in the cosmic microwave background, a kind of bruise on the sky. While the search for such a signature in the Planck satellite data has so far come up empty, it demonstrates that the multiverse is not entirely immune to observational scrutiny. Other potential fingerprints include strange anomalies in the large-scale distribution of galaxies or unexplained features in the gravitational wave background, all of which could point toward a violent beginning involving other universes. The quest is to find a crack in the wall of our observable reality, a clue that we are not alone in the ultimate sense. The debate over the multiverse inevitably spills over from the halls of physics departments into the realms of philosophy, forcing us to confront deep questions about the nature of science and reality itself. It challenges the very definition of science as a discipline based on testable, repeatable experiments. If the multiverse is true, vast portions of reality would be permanently hidden from us, leading some to wonder if we are reaching the limits of what can be known. This hypothesis also reignites ancient philosophical debates about the nature of existence. Is our universe a unique, special creation, or is it a mundane specimen in an infinite cosmic zoo where every possible physical reality is realized somewhere? This perspective can be both humbling and liberating. It suggests that the laws of physics we hold so dear are not universal, eternal truths, but merely local bylaws specific to our own cosmic neighborhood. This radical shift in perspective forces cosmologists to consider alternative explanations for fine-tuning, such as the possibility of a single, elegant underlying theory that naturally predicts the constants we observe, making the multiverse an unnecessary complication. The very existence of the multiverse hypothesis, whether it is ultimately proven right or wrong, serves a vital purpose. It pushes the boundaries of cosmology, encouraging a level of open-minded exploration and intellectual bravery that is essential for tackling the universe's deepest mysteries. It shows us that when faced with anomalies that defy conventional explanation, the most productive response is not to ignore them, but to follow the evidence, no matter how strange the path may seem, and to dare to imagine realities beyond our wildest dreams. History provides a powerful testimony to the fact that science rarely advances in a straight line. Instead, its most profound leaps forward are almost always preceded by a period of intense confusion, sparked by a stubborn piece of data that simply will not fit into the existing box of understanding. These are the anomalies, the celestial rebellions that refuse to obey the established rules. Consider the classic example that forever changed our concept of gravity. For centuries, Newtonian physics reigned supreme, offering a seemingly perfect description of the cosmos. But there was a tiny, nagging problem. The planet Mercury, the innermost world of our solar system, did not follow its predicted path with perfect fidelity. Its orbit precessed, its elliptical path slowly rotating around the Sun, at a rate that was ever so slightly off from what Newton's equations demanded. This minuscule discrepancy, just 43 arcseconds per century, was a pebble in the shoe of classical physics. For decades, it was an annoyance, perhaps attributed to an unseen planet or a cloud of dust near the Sun. But it persisted, a quiet, unresolved whisper in the data. It was this very anomaly that provided the crucial testing ground for a young clerk in a patent office named Albert Einstein. His theory of general relativity, which reimagined gravity as the curvature of spacetime, didn't just explain Mercury's orbit, it predicted its exact precession with stunning accuracy. That small, persistent failure of Newton's theory became the first great triumph of a revolutionary new paradigm, demonstrating that the universe's greatest gifts are often wrapped in the paper of its most perplexing puzzles. In the grand theater of modern cosmology, we find ourselves in a remarkably similar era of revolutionary potential. The established paradigm, the lambda cold dark matter model, is an incredible achievement, a framework that explains the universe's composition and evolution with breathtaking scope. Yet it is now surrounded by a chorus of anomalies, each one a potential Mercury's orbit for the 21st century. The Hubble Tension, the Lithium Problem, the inexplicable properties of Oumuamua, these are not mere statistical flukes to be smoothed over. They are direct challenges, forcing scientists to question the most foundational assumptions we hold about reality. Is dark energy truly a constant? Is our understanding of the early universe's nuclear physics complete? Are our categories for celestial objects too simplistic? This process of confronting anomalies is the engine of scientific progress, driven by the powerful principle of falsification. A theory isn't proven true by piling up evidence that supports it. It survives by repeatedly resisting attempts to prove it false. Every time an observation clashes with a prediction, it creates a crisis. This crisis forces a period of intense creative ferment, where old ideas are stress-tested and new, more radical explanations are born from the ashes of the old. It is a messy, often contentious, but ultimately essential cycle that prevents science from becoming a stagnant dogma, and instead keeps it a living, breathing, and evolving pursuit of truth. Navigating this turbulent process is not the work of a lone genius in an isolated lab. It is a deeply social and collaborative endeavor, a global conversation subject to the most rigorous scrutiny. When a team announces a potential discovery, like the anomalous acceleration of the universe that pointed to dark energy, the finding does not immediately enter the textbooks. It is thrown into the arena of the scientific community. Other researchers around the world immediately set to work, poring over the data, searching for any potential systematic error, any overlooked effect, any alternative interpretation. This process of peer review, for all its flaws, acts as a collective immune system defending against error and hype. It is a slow, deliberate, and often frustrating filter, but it is what gives scientific consensus its weight. Furthermore, these anomalies demand new tools. The puzzle of dark energy could not have been solved without the development of sensitive digital cameras on large telescopes and the sophisticated analysis techniques needed to find and measure distant supernova. The hunt for the nature of dark matter drives the construction of ever more sensitive detectors deep underground. The mystery of fast radio bursts has necessitated the creation of real-time, all-sky monitoring systems with immense computing power. The questions we ask shape the technologies we build, and in turn, those new tools open windows onto realities we never knew existed. This relentless pursuit of answers to cosmic puzzles naturally breaks down the traditional walls between academic disciplines. An anomaly like the black hole information paradox is not just a problem for astrophysicists. It draws in particle physicists, specialists in quantum information, and even string theorists. Understanding the potential implications of Oumuamua requires knowledge of planetary science, stellar evolution, and the dynamics of interstellar space. To grapple with the philosophical implications of the multiverse, cosmologists must engage with philosophers of science. This interdisciplinary cross-pollination is where some of the most innovative ideas are born. When experts from different fields, each with their own unique toolkit and perspective, come together to attack a common problem, they can see connections and possibilities that would be invisible from within a single silo of knowledge. The greatest cosmic mysteries are simply too big for any one branch of science to solve alone. They require a united intellectual front, a blending of minds that enriches the entire endeavor and leads to a more holistic and more accurate picture of our universe. At its heart, this entire process is fueled by two of the most valuable commodities in science: pure curiosity-driven research and a courageous willingness to sit with uncertainty. The most transformative discoveries often come not from a mission with a practical application, but from simply wanting to know the answer to a fundamental question. Why is the universe expanding faster and faster? What is the vast majority of matter made of? These are questions born of wonder, not utility, and pursuing them requires embracing the uncomfortable truth that we do not have all the answers. In a world that often demands immediate certainty, science teaches us the power of saying, "We don't know yet." It is in that space of not knowing, in that fertile ground of uncertainty, that imagination and innovation can flourish. Anomalies are not setbacks to be hidden or ignored. They are the most exciting part of the scientific journey. They are the signposts pointing toward the next frontier, the invitations to venture beyond the map of the known. They remind us that the universe is still full of wonder, still capable of surprising us, and that the greatest discoveries likely lie not in confirming what we already believe, but in unraveling the things that currently make no sense to us at all. It's a beautiful and often overlooked truth that humanity's most profound technological leaps are frequently born not from a desire for practical application, but from an insatiable curiosity to solve a cosmic puzzle. The relentless pursuit of explaining the universe's great anomalies has, time and again, acted as a powerful engine for innovation, forcing us to invent tools of such exquisite sensitivity and power that they often redefine what we believe is possible. Consider the epic search for dark matter. To catch a ghost, you need a trap of near-impossible perfection. This quest has driven the creation of detectors housed deep within mountains, in abandoned mines, and beneath vast sheets of ice, places shielded from the constant rain of cosmic rays that would drown out the faintest whisper of a dark matter interaction. These are not simple machines. They involve vats of ultra-pure liquid xenon, cooled to temperatures colder than deep space, watched over by arrays of light sensors so sensitive they can detect the single, tiny flash of light that would occur if a dark matter particle ever nudged an atomic nucleus. The engineering required to achieve such a pristine, quiet environment pushes the boundaries of material science, cryogenics, and ultra-low noise electronics. While we haven't found the dark matter particle yet, the technological journey to build these instruments has already advanced our capabilities in sensor technology and radiation shielding, with potential applications in national security and medical imaging. Similarly, the enigma of dark energy and the Hubble tension demand a level of precision in measuring the cosmos that was unthinkable a generation ago. This drove the development of the James Webb Space Telescope, a marvel of optical engineering that had to invent entirely new ways to fold and unfurl a massive golden mirror in the vacuum of space, and to cool its instruments to within a few degrees of absolute zero to peer into the infrared universe. The software and algorithms developed to analyze its stunning images are now being adapted to improve diagnostic imaging in hospitals, helping doctors detect subtle patterns in medical scans that the human eye might miss. Perhaps no single story better illustrates this transformative power than the decades-long quest to detect gravitational waves. The prediction from Einstein's theory was clear. Massive cosmic events like colliding black holes should send ripples through the very fabric of spacetime. But these ripples are unimaginably tiny. By the time they reach Earth, they distort space by a distance far smaller than the nucleus of an atom. Detecting such a signal was considered a fool's errand for most of the 20th century. Yet the cosmic mystery was too compelling to ignore. This led to the creation of LIGO, the Laser Interferometer Gravitational Wave Observatory. To achieve the necessary sensitivity, LIGO engineers had to overcome a host of seemingly insurmountable challenges. They built the world's most perfect vacuum tubes 4 kilometers long, through which laser beams travel. They developed mirror suspensions that isolate the optics from the rumble of distant ocean waves and even the falling of leaves in a nearby forest. They invented techniques to cancel out the minuscule fluctuations in the lasers themselves. It was a billion-dollar gamble on a signal that many thought we would never see. Then, in 2015, it happened. LIGO detected the chirp of 2 black holes merging over 1 billion light-years away. That single moment didn't just confirm a century-old prediction. It flung open an entirely new window on the universe. We are no longer just stargazers. We are now universe listeners, able to hear the silent, violent symphonies of the cosmos. The technological marvel that is LIGO now detects these events regularly, and its success has spawned a global network of detectors, from Virgo in Italy to Kagra in Japan, creating a new field of astronomy built not on light but on spacetime itself. The ripple effects of these cosmic-driven technologies extend far beyond the confines of pure research, creating a cascade of spin-off benefits that touch our everyday lives. The incredibly stable lasers developed for LIGO are now being used to create more precise atomic clocks, which in turn form the backbone of the global positioning system that guides our cars and smartphones. The advanced vibration isolation systems pioneered for LIGO mirrors are inspiring new designs for more sensitive heart monitors, capable of detecting subtle arrhythmias that older technology would miss. The complex data analysis techniques, including machine learning algorithms, created to sift the faint gravitational wave signal from overwhelming noise, are now being applied to improve fraud detection in financial transactions and to model complex climate systems. Even the development of the Charge-Coupled Device, or CCD, which was driven by astronomers' need to capture every precious photon from distant galaxies, is the very same technology that powered the digital camera revolution, putting a high-quality camera in nearly every pocket on the planet. This pattern repeats itself again and again. The need to see the invisible, to hear the silent, and to map the unmappable forces us to invent, and those inventions have a remarkable habit of finding essential uses back here on Earth, improving our health, our security, and our connection to one another. These grand technological endeavors, born from cosmic mystery, also serve as powerful catalysts for international cooperation and a renewed focus on education. A project like the Event Horizon Telescope, which captured the first ever image of a black hole's shadow, was not the work of a single nation. It was a global alliance of radio telescopes spanning from the high deserts of Chile to the frozen peaks of Antarctica, synchronized with atomic clocks to function as a single, Earth-sized instrument. This level of collaboration requires nations to set aside political differences and work towards a common, inspiring goal. Similarly, the International Space Station stands as a testament to what humanity can achieve when we pool our resources and intellect. These big science projects demonstrate the profound value of fundamental, curiosity-driven research, making a compelling case for public and private funding by showing that investing in the deepest questions of existence yields not just knowledge, but tangible technological and societal progress. Furthermore, the stunning images from the James Webb Space Telescope and the thrilling discovery of gravitational waves capture the public imagination like nothing else. They become powerful tools for educational outreach, inspiring a new generation of students to pursue careers in science, technology, engineering, and mathematics. They show young minds that science isn't just about memorizing formulas in a textbook. It's a vibrant, adventurous detective story on a cosmic scale with real-world impact. This synergy creates a virtuous cycle. Cosmic mysteries drive technological innovation, which in turn fosters global collaboration and inspires future innovators, ensuring that the pipeline of discovery and invention continues to flow, propelling both our understanding of the universe and the capabilities of our own society forward into an ever more promising future. We stand today on the threshold of a new golden age of cosmic discovery, an era where our tools for probing the universe's deepest secrets are about to become exponentially more powerful. The next generation of observatories now being built or in advanced planning are not merely incremental upgrades. They are revolutionary instruments designed to systematically hunt for the anomalies that keep scientists awake at night. In the dry, clear mountains of northern Chile, the Vera Sea, Rubin Observatory is preparing to embark on an unprecedented decade-long survey of the entire southern sky. Its mission is to create the greatest astronomical movie of all time, a dynamic map of the cosmos that will capture the fleeting and the variable. With a camera containing over 3 billion pixels, it will scan the sky night after night, detecting billions of galaxies and tracking the motions of countless celestial objects. This vast, flowing river of data will be a treasure trove for anomaly hunters. It will allow us to find millions of gravitational lensing events, providing a massive statistical sample to finally nail down the properties of dark matter halos and test theories like MUND with a rigor never before possible. It could discover dozens of interstellar visitors like Oumuamua, giving us a proper census of these cosmic tourists and understanding their true nature. And it will monitor the brightness of countless stars, potentially finding hundreds of new Tabby stars, helping us distinguish between exotic megastructure hypotheses and natural, if bizarre, astrophysical phenomena. The Rubin Observatory won't just look for known puzzles. It will inevitably reveal entirely new classes of variable objects and transient events that we cannot yet imagine, ensuring that the list of cosmic mysteries only grows longer and more fascinating. While the Rubin Observatory will paint the cosmos in visible light, other missions are preparing to listen to the universe in an entirely new way, through the ripples in space-time itself. The Laser Interferometer Space Antenna, or LISA, is a visionary mission led by the European Space Agency with NASA participation. Unlike its ground-based cousins LIGO and Virgo, which listen to the high-frequency chirps of stellar mass black holes, LISA will consist of 3 spacecraft flying in a vast triangular formation, millions of kilometers apart, connected by lasers. This colossal instrument will open up the low-frequency gravitational wave spectrum, a realm filled with the deep, resonant hum of the cosmos. It will hear the gentle, persistent background rumble from millions of pairs of supermassive black holes orbiting each other in the hearts of distant galaxies. It will detect the death spirals of smaller black holes as they are captured by these supermassive giants, events that will test Einstein's theory of general relativity in the most extreme gravitational fields imaginable. But perhaps most thrillingly, LISA could hear the signal from cosmic phase transitions in the very early universe, a relic from when the fundamental forces first split apart. It might even detect the faint, telltale gravitational waves from cosmic strings, hypothetical defects in spacetime left over from the Big Bang. Any of these detections would not just solve an anomaly, it would rewrite the first chapter of our cosmic history, giving us direct evidence of physics at energies 1 trillion times higher than any particle collider. And then there is the relentless pursuit of the universe's first light, a quest that is driving the development of the most sensitive cosmic microwave background experiment ever conceived, CMB-S4. This is not a single telescope, but a coordinated army of them, with hundreds of thousands of detectors planned for the South Pole and the high Atacama Desert in Chile. Its primary goal is to hunt for the holy grail of cosmology, the primordial B-mode polarization, the signature of gravitational waves from inflation. But its mission goes far beyond that. CMB-S4 will map the CMB with such exquisite detail that it will put the Hubble tension to its ultimate test, providing a measurement of the universe's expansion rate from the early universe with near-perfect precision. It will scour the sky for any statistical anomaly, any deviation from the standard model of cosmology that could point toward new particles, extra dimensions, or a dynamic form of dark energy. It will study the large-scale structure of the universe through the subtle shadows that galaxy clusters imprint on the CMB, weighing the cosmic web with unparalleled accuracy. The data from CMB-S4 will be so precise that it will either confirm our current lambda CDM model in triumphant detail, or, more likely, reveal the subtle cracks that force us toward a new and deeper paradigm. The sheer deluge of data from these and other future missions presents a monumental challenge of its own, one that is being met with a revolutionary tool: machine learning. The old methods of astronomers manually scanning photographic plates are long gone. The Vera Rubin Observatory alone will generate over 20 terabytes of data every single night. To sift through this fire hose of information, scientists are training sophisticated artificial intelligence algorithms to become cosmic detectives. These AIs can learn to recognize the subtle, non-intuitive patterns that might signal a new type of anomaly, a strange light curve that doesn't fit any known classification, a peculiar arrangement of galaxies that hints at modified gravity, or a faint, unexpected correlation in the gravitational wave background. Machine learning will also be crucial for the burgeoning field of multi-messenger astronomy, where the key is rapid coordination. When a gravitational wave detector like LIGO or LISA hears a signal, an AI can instantly cross-reference it with observations from gamma-ray, optical, and neutrino telescopes, pinpointing the source within minutes and allowing the entire global astronomical community to swing into action. This integrated, automated approach transforms our ability to do cosmic science, turning isolated observations into a cohesive, multifaceted understanding of the most violent and energetic events in the universe. This grand endeavor is by necessity a global one. The scale of the questions and the cost of the tools demand unprecedented international collaboration. We see this already in projects like the Event Horizon Telescope, a globe-spanning network of radio observatories that worked in concert to capture the first image of a black hole. The future belongs to these kinds of alliances. The LISA mission is a partnership between Europe and the United States. The data from the Vera Rubin Observatory will be available to astronomers and citizen scientists worldwide. These collaborations do more than just share costs. They pool the world's brightest minds, fostering an environment where a physicist in Japan can have a breakthrough analyzing data from a telescope in Chile, which then inspires a new model from a theorist in Germany. This collective effort breaks down not only national boundaries but also the walls between disciplines. Cosmologists, particle physicists, computer scientists, and engineers are now sitting at the same table, speaking a common language in their pursuit of answers. This fusion of expertise is our greatest asset, ensuring that the intellectual firepower brought to bear on these cosmic puzzles is as vast and powerful as the universe we are trying to understand. As we peer into this thrilling future, we can dare to dream about the revolutions that may lie just over the horizon. The persistent anomalies we face today, the Hubble Tension, the nature of dark matter, the Vacuum Catastrophe are not dead ends. They are signposts, and they are pointing the way toward a more complete theory of reality. The data from these new observatories could provide the crucial evidence needed to finally formulate a working theory of quantum gravity, perhaps through string theory or loop quantum gravity, showing us how the fabric of spacetime is woven from discrete threads at the tiniest possible scale. They might reveal that the fundamental constants of nature, like the speed of light or the strength of gravity, are not truly constant, but have been slowly changing over the life of the universe, a discovery that would fundamentally alter our understanding of physics. They could even uncover evidence for extraspatial dimensions, hidden from our everyday perception but influencing the universe on the largest scales. Every unexplained flicker of a star, every unexpected bend of light, every puzzling signal from the void is a potential key to a deeper layer of reality. The journey into the unknown is accelerating, and with each new anomaly we solve and each new one we discover, we are not just filling in gaps in a textbook. We are actively participating in one of humanity's greatest and most enduring adventures, the quest to comprehend our magnificent and mysterious cosmos. From the ghostly tug of dark matter shaping entire galaxies to the fleeting, brilliant enigma of fast radio bursts arriving from the cosmic void, we have journeyed together through a universe that is far less settled and far more wonderfully strange than we often assume. These cosmic anomalies are not mere errors in our data or simple glitches in our understanding. They are the universe's most profound and persistent questions, whispered across the vast expanses of space and time. They consistently challenge the very frameworks we use to describe reality, forcing us to admit the boundaries of our current knowledge. In doing so, they do not represent failure, but rather the most exciting opportunity for growth. Each mystery, from the unsettling Hubble tension that questions the universe's expansion rate to the stubborn Lithium Problem hinting at incomplete nuclear histories, acts as a beacon. These are not roadblocks on the path of discovery. They are the signposts pointing toward the next great frontier, compelling us to look deeper, to think more creatively, and to continually refine our picture of the cosmos. This relentless process of confronting the unknown does more than just fill textbooks. It actively forges the future of science and technology. Every time a prediction fails to match an observation, it creates a cascade of innovation. The puzzling nature of dark matter has driven us to build exquisitely sensitive detectors deep underground, pushing the limits of material science and low-noise electronics. The bizarre acceleration of the universe's expansion, attributed to dark energy, demanded the creation of space telescopes of unprecedented precision, like the James Webb Space Telescope, whose technological marvels now benefit fields from medicine to material science. The hunt for gravitational waves, once thought a fool's errand, led to the engineering masterpiece that is LIGO, opening an entirely new window on the universe and proving that our most ambitious dreams can become tangible reality. This dynamic cycle, where a theoretical puzzle inspires technological advancement which in turn provides new data to refine the theory, is the very engine of scientific progress. It is a beautiful, self-sustaining dance between human curiosity and cosmic mystery, ensuring that our tools and our understanding evolve in lockstep, each pushing the other to new heights. It is crucial to remember that the universe's most valuable gifts to us are often not the answers we already possess, but the puzzles we have yet to solve. An anomaly is an invitation, a call to adventure that beckons us to venture beyond the comfortable map of the known and into the thrilling wilderness of the not yet understood. These cosmic curiosities are what keep the scientific spirit alive and vibrant, preventing it from becoming a stale collection of facts and instead maintaining it as a living, breathing, and endlessly fascinating quest. They humble us, reminding us that for all we have learned, we are still just beginning to decipher the grand story of everything. At the same time, they empower us, showing that our ingenuity and our relentless drive to know can, piece by piece, unravel even the most complex secrets. This journey is a collective human endeavor, one that connects us across generations and across the globe in a shared mission to comprehend our magnificent and mysterious home. Now, I am incredibly curious to hear which of these cosmic anomalies captured your imagination the most. Was it the possibility of a hidden planet 9 sculpting the edge of our solar system, or the spine-tingling mystery of the WOW signal, that one-time cosmic hello that has never been repeated? Perhaps the profound implications of quantum entanglement for the very fabric of spacetime left you pondering the nature of reality itself. Share your thoughts and your favorite mysteries in the comments below. Let's continue this conversation and explore these ideas together. If you enjoyed this journey to the frontiers of knowledge, please subscribe to the channel and hit the notification bell so you don't miss our next adventure into the unknown. There are always more wonders to uncover, more puzzles to solve, and more of the cosmos to explore. Thank you for joining me on this expedition, and remember, the next great discovery is waiting just beyond the edge